of course, we can look at some key features that in normal dispersion. And in any time that we're talking about normal dispersion, we can see that the first thing that I mentioned, that refractive index increases as wavelength what decreases. And it's the first thing I've mentioned in the slide here. Refractive index increases as wavelength what decreases. The second thing that we have to look at is the rate of increase, that is looking at the slope, is greater at short wavelength. Is that okay? And the next thing is every material behaves differently. It doesn't mean that if we have a crown glass, and we have a flint glass, they should behave the same, as in have the same refractive index or behave the same in terms of wavelength passing through. No, every material has its own way. And another thing is each material has its own curve. Is that okay? So I brought some charts in here to explain each of the key features of a normal dispersion. So please, all these things have to be in mind, the key features for a normal dispersion to happen. The first one is the refractive index increases as wavelength decreases. Is that okay? So I want to look at something like this. But anyways, are you following? Should I go on?
Yes.
Okay, great.
Yes.
So now let's look at something here. So one key feature that we just mentioned is the refractive index increasing as we have a wavelength decreasing. Now when you look at this chart, this is an experimental chart, is okay, and values that have been taken. Now each light represents, of course, our wavelength. Is okay. So we have a violet, we have a blue, we have a green, we have a yellow, we have an orange, we have a red. Now, and it has its values down here, and it's represented by Armstrong. Armstrong is 10 raised to the power negative 10 meters. Is that okay? So they are all represented in Armstrong. That's our wavelength. That is the color wavelength in quote. Now, when you look at something like this, and we have some different substances. Is that okay? So we have the crown glass, we have the flint, light flint, the dense flint, the quartz. We mostly use the quartz. The diamond, we have the ice, we have the strontium, we have the rutile, and they all have different refractive indexes here. Is that okay? So when we take a typical one like the crown glass, the first one, it has about 1.5380. And the most important thing here is we are saying refractive index increases with what? Decreasing wavelength. Now, when you look at what is going on here, if you want to relate the decreasing wavelength, it means you have to start from red and go to violet. Is that okay? So you can see that red is big, it goes to red, orange, it goes to yellow, and it is going down. You can look at the values. You see the values goes down. Is that okay? Now, let's relate the values that is going down, that is the wavelength, with respect to the refractive indexes. Now, when you look at the refractive index of the first material here, that is the crown glass, you can see that as we have 1.52, it increased a little. Is that okay? To 1.5216. It goes again to 1.5225. It goes again. So it will be increasing with that respect, with the what? The wavelength that we have here. Exactly. So red has a bigger wavelength as compared to violet. We start with the refractive index here. It is smaller as compared to the very last one that we have here. Exactly. And this is not for only one material. It behaves the same in almost all materials that is experimentally checked. Is that okay? So this actually explains the first property of a normal dispersion. That is what refractive index increases as wavelength what decreases. We can check the second material too. The same. So here, if it's going from red to violet, it is decreasing from the values beneath it, right? Now we check the refractive index of, let's see, the second material here. That is the light flint. You can see that, maybe let me start from the red here, the down here, exactly. It's 1.5850. Then it will increase a little, 1.5867. It will increase again, it will be increasing, exactly. So you can see that The red from here decrease, but the refractive index what increase. Is that okay? Or we can say that the refractive index decrease and the wavelength increases. Is that okay? But whatever being the case, know that they are not going to increase the same or decrease the same. One is supposed to increase as one decreases. Is that okay? Which is very important. And we spoke, these are all recap that we did last week. Oh. And we also spoke about the fact that if we have uh, uh, different materials, they will behave differently, which is very evident. Now, let me go back a little. Even this chart can explain that. That is, we have different materials here, and all their refractive indices behaves differently. Is that okay? When you are relating it to wavelength, they all have different refractive indices. So this chart can explain, and this chart too can explain that. And when you look at this chart, we have different materials again. We have the telescope, we have the telescope crown, we have the bronze silicate, we have the barium, we have the vitreous quartz, and this is their normal dispersion value. So this is what we have here down here. And you remember we said for a normal dispersion, you're supposed to get less than 0. So that is why we have the negative attached here. Exactly. So all the values here, they are negated. And these are their refractive indices. And for borosilicate crowned to, these are their refractive indices and their normal dispersion. Is that okay? And when we look at this, what we have here is our refractive index. Is that okay? Again, in Armstrong, and I said Armstrong is 10 raised to the power what? Negative 10 meter. Is that okay? So if I write a value in an Armstrong, you're supposed to understand the wavelength I'm talking about here. Now, if we have something like this, it's quite easy to relate these two. And I don't know if someone can help me here. I want to use the first key feature to explain this. Is it possible? And this is the first key feature. Refractive indices increase as wavelength decreases. I don't know, can we observe that here in this chart? Hello, are you online?
Yeah, yes, sir. We can see.
Or you are observing. So observe it for a minute and
So
try and
for
see. So from the chart here, I've explained that the chart here, the columns here represent, the two columns here represent this material, the telescope
mm,
crown, and the blue silicate, and the barium
mm,
flint, is that okay, and the vitreous quartz. Now,
mm,
each material has its respective refractive index
and
and a
then the
normal,
wavelength. Mm,
no, this is a normal dispersion, is that okay?
okay,
So
okay,
refractive index and a normal dispersion, refractive index and a normal dispersion. But the last
okay.
column here, sorry, the first column that starts here is a wavelength. Is that okay?
Yeah.
That is for C, D, F, G, and H. Is that okay? Has their respective wavelength. But I want us to see if we can relate these two parameters. We have about 3 parameters here. Sorry, we have about three
Sir,
parameters. Mhm,
so the C, D,
mhm.
E, and then F are they different wavelength with respect to the materials?
Very good. So they are
Okay,
different wavelengths, not with respect to the material, different
okay,
wavelengths with respect to their refractive indices and
okay,
normal dispersion. Is that okay?
okay,
So
okay.
when we have, say, the C has 65, 63, and we can see their refractive index is different, their normal dispersion is different. And when you go to D, their refractive index too is different as compared to the normal dispersion. The same way going on. But now let's forget about the normal dispersion. That is the negative D
That your screen
change
is
in
gone.
my screen is that what?
It's gone. I can't see it again. Or it's
Is
only
it
me.
the same for
Oh,
you?
check your network. I can see it.
Mm, check your network for me. So maybe let me go back and explain this one. So when you look at this chart like this, we have wavelength at the top here. Is that okay? That is violet, blue, green, yellow, orange, and red. And they all have their respective wavelength number. Is that okay? So red has 6600, orange has 6100, yellow has 5800, green has 5500, blue has 4700, and the same as violet. Violet has 4100. Is that okay? So different values. But you see, when you want to travel from violet to red, you can see that the wavelength increases. Is that okay? But if you want to travel from red to violet, you can see that the wavelength decreases. Is that okay? And we've been given some materials. And for each material, we expose the wavelength to it and measured a respective refractive index. So anytime we have a material like a crown glass and we expose it to, say, a red wavelength, we get 1.5200. We expose it to orange wavelength, we get 1.5216. Is that okay? The same as the yellow, we'll be getting different values. But we want to look at the values behavior with respect to what? Their wavelength. And when you observe the first one like this, I want to travel from red to violet. You see, as we are traveling from red to violet, the wavelength decreases. Is that okay? Now, if we are at a material like the crown glass, what happens to the refractive index? Maybe let me ask that question. Is it the same? Are we getting the picture I'm trying to paint here? Hello, am I online?
Yes, please.
Okay. But are we getting the picture I'm trying to paint here? Or I should go over again? Seb watching.
Yes, please. Go over again for us.
Okay. So I'm going over again. Abaseb watching, you were here last week. Oh.
Yes, I was here. Just that
Mm,
the second table, I'm a little bit confused where you have different parameters.
mm, mm.
But as for this one, I think I'm okay.
Okay. So now let me go through. I want to see if I can. So hold on. I want to make the slides big. Stop presenting. Then I'll present again. Okay, I'm showing something. Can you see?
Yes, sir, we can see.
Perfect. So now this is the picture that I'm trying to paint. When it comes to normal dispersion, we are given some 4 key features we have to abide with. And it's not an assumption, it's a practical thing that has been done. Is that okay? But we have to understand all these 4 features. Is that okay? And the first feature in a normal dispersion is anytime you have a refractive index increasing, the wavelength is supposed to decrease. Is okay. That is the very first feature. Now, there's an experimental values to actually hold on to what is going on. And the first table here is a very practical example of what is being said here. And the first one is anytime we have, of course, a refractive index increasing, we should expect a decreasing wavelength. Now, the charts that we have here, the top here represents the wavelength. Is that okay? All the values that you see down here represent the refractive index. Please, can I go on?
Yes, please.
Very good. Now, if we have this, it means that it's going to be quite straightforward here. It means that we have to look for a relation between these two. Is that okay? And that is the most important thing that I'm looking for here. We have to look for the relationship where we have the increment of this refractive index and the wavelength decreasing. And now let's look for the first material that we have here. That is the clown glass here. You see here, these are their refractive indices. Is that okay? The first row. Now, when we look at the wavelength I have at the top here, it decreases from red to violet. Is that okay? So these are their values. You can see that 600, 6,600, it will decrease to 6,100, 5,800, and it's decreasing in that order. But when we step down to the refractive index of the first material, we can see that the first material, this time around, the refractive index is increasing. Is that okay? So here, wavelength decreases as refractive index decreases. Refractive index increases. Is that okay? So we can see that the wavelength here, it will decrease, 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 decrease. And their refractive index here, of course, it will increase, 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 increase. Is that okay? We just want to observe what the key feature of a normal dispersion is telling us, whether it is, of course, correct or wrong. Is that okay? And this is a very typical explanation of what is going on. That anytime you have a wavelength, and of course it is decreasing, our refractive index here tends to what? Increase. Am I still confusing you?
No, you're okay, sir.
Very good. And this behaves the same in all materials. When you take the flint material like this, it's the same. It's okay. So I'm starting from the back here. You can see that when we are at 1.8, 1.5850, the refractive index will keep on what? Increasing. Is that okay? And here, the red here decreases. Is that okay? So always what you have to put in mind is anytime we have refractive index increasing, our wavelength tends to what? Of course, decrease. And the question came to this end, that if that is the case, can this chart actually explain the fact that if we have a refractive index that is increasing, the wavelength will decrease? That is the question that I want to ask the class.
Sir, please come again. Please, I just.
So if you just joined, it will be very difficult for you to understand what is going on. But the question for the class is, we want to see if this principle, as refractive index increases, wavelength decreases. We want to use this chart to explain, because I've used this chart to explain that feature already. I want to know if the class understands what I just said. So I want us to use this chart to explain that feature. Is it possible?
Yes, sir. It's possible.
Okay. Can you help me, Sir Francis?
Yeah, so the material C, okay. We are looking at the wavelength and the refractive index. Let me begin with the first one, which is the refractive index. We have 1.52441. And the wavelength is 6563. Now, as the same material, as the refractive index increases from to 1.5249, now the wavelength now comes down to 6439, the same material.
Perfect. Perfect. So you see, as we go down, that same thing happens. Is that okay? And it's not only for telescope count. The borosilicate also behaves the same. Is that okay? Which is very important. Now, it means we understand the first feature. Let's look at the second feature, the rate of increase of this slope. That is the change in n over the change in wavelength. Say, I don't know. He just joined, he asked the question then. I don't know if he can follow up. Sir George, can you try and follow up?
Hello, sir. You said, can I try and?
Yeah, try and follow up. He just joined, so try and follow up here.
Oh, don't worry. So I'm here.
So
Okay.
then I want to bring in the second point here. The second point is the rate of increase of, that is the slope of change in n and the change in what? The wavelength. If it's greater, you have a shorter wavelength. So you can observe this one too here. And that slope of change is what you are talking about here. This one is okay. So the change in n over the change in what? The wavelength. So anytime you have
Please,
these
are
values,
you presenting a screen? I still can't see. I've been trying.
Madam,
okay.
please, it's clear.
I've been going off, coming, but still I can't see anything.
That's clear.
Okay.
So anytime you have this change increasing, the second feature is telling us that you have a shorter wavelength. And it's very evident here. So you can see this one as it's increasing down here, the slope here. The wavelength respectively also what? Decreases. That is, it moves to a shorter wavelength. Is that okay? And of course, the third feature can also be used to explain. This chart can be used to explain the third feature, that as different materials all behave differently in this. Is that okay? When you take the values for the telescope ground, it's not going to be the same as the borosilicate. It's going to behave differently. Is that okay? So as at this chart can in fact explain the first feature, the second feature, and even the third feature. Now let's look at something here. The third feature is okay. And this feature was telling us that every material has its own curve. Is okay. So there were a lot of materials that was experimented on, and we have different materials of different wavelengths that is being exposed to with respect to the what refractive indexes. So say we take a quartz and we expose it to different refractive indexes, and we will be measuring their what refractive indexes. Is that okay? And it's true. All these materials has different what curves on their own. Is that okay? Yes, so this one.
Okay, so the previous slides.
Mm-hmm.
So if you can go to the previous slides for a minute, please.
This one?
Please, yes, please. So the negative value over there will not be considered when you are looking at decreasing or increasing, because for negative figures, the smaller the number, the higher it is. Or we shouldn't. And that's my thinking.
I explained this one earlier that anytime you have a normal dispersion, mathematically, you should expect a normal dispersion to be less than 0. Is that okay? So ideally, all dispersive material has a normal dispersion to be negative. And it's even evident in this chart. The chart I showed and even the curve here. If you have a curve like this, you find their slope, you are going to get a negative. Is that okay? So their negative here will not affect the rate that you're comparing here. Is that okay? It's an important parameter feature for a normal dispersion, how it behaves. Is that okay?
Okay.
So this curve actually, so I'm continuing. This curve actually explains the fourth feature for here, for us here. Is that okay? So in your manual, all these charts are in there, and it explains their different features and how experimental ways can also back it up. Is that okay? So it's very important. Now, when we look at all these features too, we can also, I think this thing I've explained it before, but maybe let me just go through. Every material, of course, behaves differently when absorption and emission happens. The same way these materials to, when it comes to the range where their dispersion happens to is different. Is that okay? So when we take their wavelength like this, when we take something like a crown glass, in fact, for a normal grating, we expect it to behave something like this. We're supposed to get our emission bands around this end. And I told you that we have absorption and emission band. And if, say, a gas, light passes through, say, a gas, it will absorb some and later re-emit it. I showed you earlier, we'll still be looking at it though. So for a normal emission, we have different material behave this way. That is one thing. But we also have an experimental chart that if we have different materials, how is their absorption and emission band going to behave? And when you look at something like this is for a normal prism. Is okay. The last one that I have here. And this is their wavelength increment. We have 4,000 to 7,000 here. And different materials to you want to observe how it's going to happen. Is that okay? And when you look at a very typical one like a clown glass, almost behave the same as a normal one, but even relatively in between here, it changes a little bit. So you can see where the 500 is. That is not where 500 is here. So it gets enlarged a little. And when you take something like a flint one, flint behaves almost the same, but it still shifts a little. Is that okay? So this particular chart also explains that, of course, yes, when you have different material, you may have different behavior from the material. Now, there's an experiment and thing derivation of an equation that, of course, we can say is an empirical equation from this man, the coaching, Augustine coaching. Is that okay? So he also did a very wonderful work that if I have, say, a wavelength, I can also use it to determine the refractive index of the material. And this is not per assumption. This is per, say, doing some experiment to bring out some constant so that we can use it to do that. And the very last thing here can be negligible one way or the other. Most of the times when we are calculating, we use only the two terms here. Now, if we have this kind of an equation, of course, where we have our refractive index to be A plus B over the wavelength squared, I told you that the last one here is mostly neglected because it's mostly negligible. The value here is very small. Is okay, so you can mostly ignore it. And you want to find the dispersive, the normal dispersion. Now you know that normal dispersion is always dn over what our d wavelength. Is okay. That is the change in the refractive index over the change in wavelength. Is okay. If we find the derivative of this, we're supposed to get the 2b over what our changing, our wavelength cube. Is that okay? And as of now, you understand the negative, so I'll not go there. There's a question here that we can try under coaching, but we'll do that later. Is that okay? We are far behind time, so we'll do that later. So that is how a normal dispersion is supposed to behave. But you see, interestingly, how Kochi predicted that his material to behave is not behaving that way. Of course, where we have, okay, so if we have a material like this, we expect that anytime the refractive index increases, we're expecting the wavelength to decrease. It's not behaving that way. So in anomaly, there's something that came up again, which we call the anomalous dispersion. Is that okay? Where this time around, instead of having the normal behavior as in a shorter wavelength and a longer, increase in wavelength and, increase in refractive index and decrease in wavelength, it turns out to be different when at a different band of a wavelength. Is that okay? And this time around, instead of getting it this way, when it reaches a particular band within the wavelength, there's an infinity drop there. Is that okay? So this is how we expect our curve to be behaving. But when it reaches a particular band, it doesn't behave that way again. Is that okay? So it means our Cauchy equation cannot be used to calculate some wavelength bands. It may give us wrong answer. Is that okay? So there are some limitations under Cauchy's equation, and that is where this term came in. That is the anomalous dispersion. Is that okay? And the whole thing is, yes, if we have a material, of course, and its wavelength at PQR, that is fine. But immediately we tend to enter within this end, get into the infrared. That is where we have something called the absorption band. And here, the normal behavior that we expect our curve to behave doesn't behave that way. Is that okay? In fact, as at that time, it was predicted that there's an infinity drop. Like, we don't know what is going on there, but we know that there's a drop, a drastic drop that is going down there. Then fast forward, there was one experiment that was done under this anomalous dispersion, but RW in 19s. And what he did was very simple. You know a slit now. The last time I explained a slit to you, and he placed a lens here, he placed another lens here in the chamber, and he has sodium in this chamber, and he heated it. Is that okay? To just get the gas. Now, if we expose this light through this material, we expect that the gas in there will either absorb or emit some of the light sources for us, which we will come back to that. Then he placed another slit here to a spectroscope. Is that okay? This time around, we call it a spectrometer, so that it will disperse the light for us, so that we will observe what is actually going on there, whether we are going to get some wavelengths being absorbed or some wavelengths being re-emitted, or all the light source is going to go through. Is that okay? So supposing no material is here at all, we expect that all the light we pass through the slit here or illuminated through the slit here supposed to be photographed here. Is that okay? You're supposed to observe all the light source here, all their wavelengths. You're supposed to observe it here. But if we have a material here, it means the material here will absorb some of this light source or re-emit some of this light source. Is that okay? And it is through this that he got to know that, yes, even if under this anomalous dispersion, there's also some limitations there, where we can use an equation here to solve what Cauchy's equation limitation breaks up to. Is that okay? Because Cauchy equation just ended to the fact that if we have some wavelength, there's a drastic drop. It's not going to behave the normal way, and that is within the infrared region. Is that okay? So he brought this equation here to solve our issue, where we have the n squared to be equals to 1 plus a, that is another constant, multiplying the wavelength square divided by the wavelength square minus the wavelength not what squared. And here we are just talking about the natural frequency and the normal frequency. Is that okay? Now, have I managed to confuse you enough, or we should go on?
Please, you can go on.
Okay. So now, if we have different materials at different refractive indices, it may behave differently. Is that okay? So if, say, we have our material and it's within this wavelength range, per the equation, we expect it to behave around this end. And per the equation, if we are within this wavelength range, we expect it to behave this end. And of course, if we are within this wavelength range, we're supposed to behave this way. Is that okay? If what was going on here? Okay, so if we do that, it means the intensity and the velocity and other things supposed to also change. Is that okay? And this is actually just showing the fact that absorption actually have a very strong effect on dispersion. Is that okay? And even with the anomalous dispersion too, it has its own limitation one way or the other, because there was also a proof where we were able to find out that yes, even if we have a particular absorption range within the wavelength, there's no infinity absorption that is going on within the range. There's an absorption, exactly, which is very dependent on the absorptance of the material, exactly. So whatever being the case, yes, it's going to absorb. The material may absorb within a particular range, exactly. So where we have an absorptance that is going high, we have a very particular behavior of the material within that range, and that is all, exactly. Unlike the one that we saw earlier, where you can see that this end here just drop out drastically, and we don't know where it is ending exactly. But there's a limitation to that. Okay, yes, it drops, but it has even a range that it drops to, and it just fall back to normal. Now, if we can prove this, it means that it's easy that there can also be an equation to buttress what is going on here, exactly. And that is where the Helmholtz equation comes in to help us with that, exactly. And here, what it's considering in this is three important parameters. That is the damping plus the oscillator and the energy loss, and of course, the absorption coefficient. We'll be looking at this equation again in the absorption end. So this one will, I will explain it very later at the latter part. Is that okay? I think these things we've done it all, so it's just still a recap, still under unit 3. So we have to double up. So in terms of our dispersion, we can also look at something we call the continuous dispersion, and you can look at discontinuous dispersion. And this is just relating the different wavelength band and how they behave within different range of dispersion. So when you look at something like, say, if you have the if you have something like the X-rays have a discontinuous dispersion. And when you look at some different form of, say, the electromagnetic spectrum, it has a continuous forms of what? Dispersion. Is that okay? So if you remember from X-ray, we go to the ultraviolet, we go to the visible, we go to the infrared, we go to the radio waves. Is that okay? So you see, all the materials have its own behavior. All this while we will only looking at the visible, is that okay? And we just check their limitations and their delimitations and some of the equations that holds up to it, is that okay? But when observing all of them in different wavelengths that we know, that is the electromagnetic spectrum, you can even see that some of these wavelengths may behave as a discontinuous one, and when it reaches a particular end like this, we get a very continuous one. Is that okay? So that is continuous and the discontinuous. Now, I've explained this. Now, I want to talk about the unit 4, what we're supposed to do today, actually. And today, I just want us to go through the general, and we're talking about absorption in general, absorption and scattering. But the first session is talking about the general and the selective absorption. Then we talk about the distinction between the absorption and scattering. We talk about absorption by different materials. And we're supposed to look at fluorescence. I don't know why the model actually arranged it like this. This one's supposed to come here. Then let's say the fluorescence will be the last or something, because when it's messed up like this, it is very confusing. But anyways, let's try and see if we can go through together. Can I go on?
Yes, please.
Okay. So now, if you remember, I told you that when light is incidented on a material, say any matter, a lot of things do happen in there. So if you have incident light, we've looked at one property called reflection. We've looked at one property called refraction. We've not done the emission, but we are yet to do scattering and absorption. Exactly. So when light hits on the material, a lot of things happen. Yes. So it could be that the material can just reflect the light it gives to it, or the material can absorb some and leave some, or the material can let the light enter and say burn it, or the material can, of course, let it enter and scatter everything. Exactly. Or the material can absorb it and change it to other form of energy for us. Exactly. So a lot of things will happen. And one thing that mostly happens is the absorption and scattering. Is that okay? And that is what I want us to look today. In fact, I've only prepared slides on Unit 4. So if you're able to finish up before time, we will just end the class. Then the last meeting that we do, we'll look at Unit 5, Unit 6. They are not plenty, so I can still cover up. Is that okay? So we use the first 2 hours for Unit 5 and use the other 2 hours for Unit 6, and that will be all. Okay. So now let's go on. So in simple terms, when you are saying absorption, we are just talking about the fact that light loses its intensity when it's just travel deeper in the material. Is that okay? And when it absorbs this light, it can of course convert it to different form of energy. And as far as it's absorbing it, it means the light intensity tends to what? Go down. Is that okay? And it's like what should I use to explain this? It's like light trying to pass through water, maybe. So you see, when you are inside the water, the intensity of light that you may get may be different from when you are outside water and direct to the sun, to the light. Is that okay? So it means when light enters the material, it will tend to what? Absorb some of them. And as it's traveled to, the intensity of the light what tend to what, of course, reduce. Now, each other component is the scattering. So the scattering is not very dominant, but it do happens a lot of time. And what it's saying is just redirecting the light to different forms. Is okay. It is not ready to absorb it. It is not ready to convert it to different form. But each one is when the light comes, it will redirect it. Go to this angle, move to this angle, move here, go here. That is what the scattering is doing. Is that okay? Now, under absorption, we have something we call general absorption and selective absorption. Under general absorption, we are talking about when light absorb light, when the material absorb light in a general form. Is that okay? When I say general form, in a general intensity wise. So let's say you know that white light composed of all these colors. Is that okay? Now, supposing we give this white light to a material like this. Is that okay? Instead of it to say absorb some of them and leave some of them to go. No. If it's absorbing 20%, it will absorb 20% of all the wavelengths. So it will absorb 20% of the red, 20% of the orange, 20% of the yellow, 20% of the green, 20% of all of them. Is that okay? And it allows the rest to go. So here, it doesn't absorb a particular wavelength and leave some particular wavelength to go. And please, throughout this section, when we are talking about absorption and scattering, wavelength is very important. So imagine wavelength being mentioned here as different light sources. Exactly. No, different light colors. Let me say it that way. Exactly. So the red, the green, the yellow, all the colors that you can think of. Exactly. They are all under different wavelength of colors. So the general absorption is just absorbing all of them generally, like in equal amount. Is that okay? So it will absorb all of them in equal amounts and then allow the rest to go if there's a need. But the most important thing is general absorption, absorb all of them at in general equal amount. And in with our eyes, when general absorption happens, we may see the color to be gray. Exactly. You don't see it as white. You may see the color to be gray because it's just kind of reducing the intensity or the brightness for us. Exactly. But roughly is the same amount. The other one is selective absorption. Exactly. So selective absorption is the material tends to absorb some particular wavelength and allow some of them to go. Is that okay? So say the material may absorb, say, red, green, and allow some of them to go. It will not absorb a general one of them, like all of them, absorb all of them piece in equal amount and allow all of them to go in equal amount. Is that okay? So here it will absorb some particular wavelength, allow some of them to go, absorb some particular wavelength, allow some of them to go, particular wavelength, allow some of them to go. And again, the particular wavelength absorption you are talking about is a different wavelength of colors. Exactly. So like green, and I allow the rest to go. Like yellow, and I allow the rest to go. Okay, service mark, your hands is up. Hello, service mark.
Yes, sir. Please, the previous slide. So the previous slide. I want to show you something there. So it means about all the three diagrams, right?
Come again. You said what?
The two diagrams, all the diagrams. The general absorption is talking about all of them, man.
No, really. So the general absorption is talking about only the middle one.
The middle one.
Yes.
Oh, okay. But you were saying to absorb some percentage and allow something to pass through. So I am looking at the first diagram in that respect. And then the other one is not rather reflecting back by the diagram.
Okay, so that's a good question and a point you are bringing up.
Yeah.
The first diagram is talking about transmission, like the lens we wear. Supposing it's a transparent material that you are talking about here. So if the white light is coming in here, this transparent material may absorb some amount, but it's going to absorb equal amount of all the wavelength colors and allow the rest to go through it. Equal amount. The second one is still under general absorption, but this time around it's an opaque material. Is that okay? And this time around, if it's an opaque material, of course, it's not going to allow anything to pass through. It's going to, of course, say reflect or scatter them. So, and all the wavelengths hit on the surface, and it will absorb all of them in equal amount and allow the rest to go. But as to where it is going, that is not of interest now, because it could be that it's scattering or reflection or anything. Is that okay? But what is of interest is absorbing all the wavelengths at equal amount.
Okay.
Use the last one to explain.
And the third one.
Come again.
The third one. The third one.
No, the third one, we can't use it to demonstrate here. I'll bring it up later. Because the third one is absorbing all of them.
Okay.
Is that okay? So it's absorbing all of them. If someone may define the third one in a way that it absorbs all of them completely, one way or the other. Is that okay? The general absorption, the most important thing is it's reducing the intensity of wavelength at equal amount. Is that okay? So the selective wavelength is the opposite of the general wavelength, where it's just talking about this time around, it will absorb, but it will absorb some particular wavelength colors. Is that okay? It's not going to absorb all of them roughly at equal amount. It will absorb them in particular ones. So it will absorb, if it's green that is interested, it will absorb only the green and allow the rest to go. Or if it's the yellow that it doesn't like, it will absorb everything and allow the yellow to go. Is that okay? That is the most important thing here for the selective absorption. And in fact, the selective absorption is very, very common as compared to the general absorption. Is that okay? Because of how materials actually behave. Most materials behave in such a way that it will do a selective absorption. And I told you the last time that is why we see different materials in different color forms. Is that okay? So we see green because of how the material is behaving, absorbing the light that is incident on it and allowing some particular color to go out. And we see it in our eye as that color. Is that okay? Now, under the selective absorption, we can actually consider this thing in too many forms. So that is what I've just explained. Say, if we have some particular materials in our eye, we see the material as green because, of course, it reflects on it and allow the green to go. We see the material as yellow because it reflects on it, absorb all the colors and allow only yellow to go out. Exactly. But this one you know, so I'll not stress plenty here. When you look at some material in some special cases like a metal and a pure glass, like the lenses that we wear, you see that we are able to see anything or light is able to pass through, let's say even 100%. Is that okay? Ideally, to us, it's not absorbing anything, which I will explain later. It's not absorbing anything. So like pure glasses, like any material that you can think about that are not doped, you can see that it allows most of the light to pass through it exactly. And even some metals, they are they have a very strong reflective surfaces to the extent that if it hits on it, we get this colorful looks on it too. Exactly. And that one too has a particular color that is given to us one way or the other, unlike the doped one. Now, as I was explaining with the pure materials, like the undoped ones, we can see that some of them ideally in quotes that it doesn't absorb anything. But fun fact is it absorbs something. Is that okay? And maybe you've not seen quartz before, but when you come for practicals, I'll show you a quartz cuvette. And the quartz here is so transparent to the extent that that is what we use for experimental measurement. And interestingly, the quartz too has a particular wavelength that it absorbs. When you see the quartz, you may think that every light wavelength can pass through. But interestingly, it doesn't behave the same. It doesn't behave like that. Is that okay? It has a particular wavelength that can actually what absorb. Is that okay? So what I am trying to say is every material has a particular wavelength range that it may react to. Is that okay? So it could be that for the visible, everything is passing through. But for all you know, when you look at, say, the infrared or the UV region, it may absorb some light in there. Is that okay? So it is very important to know that. Now, when you're talking about absorption, there are about some three parameters that is very important in the medium. Is that okay? So absorption is very, very influenced by one, the concentration of the molecules in there, two, the path length, and three, we call something the absorption coefficient. Exactly. So if I have, say, a light source here, it has all the wavelength colors here nicely. I have my samples here. Now, if it passes through the sample, we see that it's not all of them that reaches this end. Some of them are no more. Some of them, they are there, but it's reduced. Some of them too is there, but it's a little bit increased. Some of them too is represented as the same. Exactly. This is what we are talking about. And we are saying that the material in between here is influenced by one, the concentration that is causing this absorption. And the path of the material, when you say the path, the diameter here is okay, the distance here. So it means that if the material I increase the distance up to this end, absorption could be high. Is that okay? Because there are a lot of space and molecules there to absorb, and the light is actually also traveling a very long distance before it reaches the detector. Is that okay? So it means when I have a long path, of course, absorption is going to increase. And the last thing is the absorption coefficient. Is that okay? Now, these three parameters are very important. And anytime we are looking at this one, we can actually look at it in respect to, imagine we have, maybe let me draw this. We have a cylinder, and one cylinder has, see, a distance like this, and another cylinder has a distance like this. And here we have our light source passing through this end to this end. And we have our light source also traveling from this end to this end. For a cylinder A and a cylinder B, which one will absorb more light, ideally?
Cylinder B.
Cylinder B, perfect. Is that okay? Because if we have thicker container, of course, we expect more light to be absorbed. Now, there are two laws that can actually govern this. The first thing is the Bayes law, and the second one is the Lambert's law. And together we call it the Lambert's law. Is that okay? Now, if we have a concentration And that wants to relate. In fact, the best law talks about concentration, and the Lambert's law talks about the distance that we've just explained. Exactly, that is the path length. Now, if you're talking about concentration, there are a lot of experiments that has been done where we use the concentration here. Let me use a laser pointer. Where the we use this kind of a formula to find the concentration in the material. So supposing we have a light source, we have a photo detector here, and of course our material is in between. Light passes through, it detects, light passes through, it detects. If the concentration in this liquid increases, you expect the absorption to also what increases relatively. Is that okay? The same way if you have incident light on a material, this is a quartz cuvette, is that okay? In a material, and we increase the length of the quartz cuvette, most of the times it's about 1 centimeter. Is that okay? So 1 centimeter cube. If we increase it to say about 2 or 3 or 4, we expect the absorption of course to also what increases. Now, there are a lot of formulas that govern this, and they are kind of interrelated one with the other. Now, if we have something like the absorption, we can absorption and transmission can be related. Is that okay? And when you're talking about transmission, let me go back a little. When light passes through a liquid, the one that we get it at the other end, we call it a transmitted light. Is that okay? The one that is reached and is inside the material here is the absorbed light. Is that okay? So we can relate the absorbed light and the transmitted light easily. Now, if we want to do that relation, so we have the absorbed light here and the transmitted light here. So it's related by the negative log of the what? Transmitted light. Exactly. So anytime I want to find the absorbed light, what I have to do is to find the negative of the transmitted light. So supposing we do an experiment and we have a device to measure the light here, we have the device to also measure the light here, and I'm able to get a transmitted light. If I find the log inverse of the transmitted light, of course I can find out what? The absorbed light. I can know that, okay, the material absorbed this amount of light. Am I confusing you or we are following?
We are following, sir.
Very good. So it is very important. But before we can get the transmitted light, we have to know the incident light and we have to know the transmitted light intensity. And when you say the incident light intensity, we want to know the intensity of light that we are initially coming to expose it to the sample. That is going to be our I naught. And when the light passes through the sample, something will go on there, selective absorption will go on there. We want to measure the intensity of it too. Is that okay? And intensity is very important. Intensity is the photon count. And you see, it's like when you go to a stadium have something they call the floodlight. That big light that is there, they used to play matches in the evening. And that light, in fact, you can't stand in front of it. It's super bright. And you know, supposing you place that light there and you are approaching it, the more you approach it, the more your eyes will hurt. Is that okay? If you want to watch it, is that okay? It's like even the sun. Sometimes, I don't know if you can get closer to the sun. You get closer to the sun, the more your eye will hurt, of course. I want a relative example. So let's still on the floodlight. When you place it there, when you get close to it, the more your eyes will hurt because the intensity is increasing. Exactly. So you approach it, the intensity increases. You approach it, the intensity increases. You approach it, the intensity increases. If you tend to move away from it, the intensity will go down. So you can think about intensity as photon count. Your eye is measuring the amount of photons that is entering it. Is that okay? So as you're approaching it, your eye photon count becomes too much. It can't read it again. You just see white, very bright white. Is that okay? So it is that is what intensity is doing. Intensity is just measuring photon count. Is that okay? So if we are about starting the measurement, we will read the photon count of the incident light if we know. So supposing we are using only red wavelength and we measure the intensity count of say 5 after passing the light through and say the intensity count reduces to say 2. This was 5, so it reduces to 2. It means that our transmitted light intensity here, the I naught, the I, sorry, becomes what? 2. And the I naught here becomes what? Becomes 5. Then if I know the I naught as 5, the I as 2, I can use it to find the what? The the absorbance. Is that okay? So because I know that this is going to be 5, this is going to be 2, and that is all. Is that okay? And if I want to find the transmittance, the only thing I have to do is to divide the I over the what? I naught. And I'm good. Is that okay? Because the transmitted light is going to be 2 over the 5. And I'll get my answer. There's another relation as a Bell-Lambert, which I just explained, where Bell-Lambert relates 1, the concentration, 2, absorption coefficient, and 3, the path length. Is that okay? So it's just related as what we just went through. The absorbance, all of these things is absorbance A. Is that okay? Absorbance equals what? The absorption coefficient multiplying the length times the concentration. Now, if in chemistry, most of the times, if you want to relate this thing, they mostly replace it with something we call the molar absorption coefficient, which is the same. Is that okay? So we can also replace it by molar absorption coefficient. I just added this thing up so that in case you see it somewhere, you'll not be confused about it. Is that okay? But the Lambert's law too can be related in terms of intensity, the light intensity that I just explained, the I. And if you know that if you have the light intensity, we can actually find the exponential of it. So something like this, if you have I naught over I, and we have this, we are interested in making I the subject. Is that okay? So it means it's going to bring a negative. So when you change this one, it means a negative has to come here. And of course, the negative can be changed to this end. Then we will get something like a log I over I naught negative our absorption coefficient LC. Is that okay? And because you want to remove the log, you will just find the exponential of this whole thing. Then at the end of the day, you will get I because I naught our exponent on negative alpha, or that is our absorption coefficient multiplying the L in C. Is this difficult? Are we appreciating it a little?
Sir.
Yes, sir.
Yeah, please. The source of the negative. The negative in there.
Okay, so I am saying that let me use a pen. So you see this term that we have here, this term. This term can also be written as negative log. This time around is going to be I on I naught equals our absorption coefficient LC. Do you understand this thing when I do it this way?
Yes.
Is that okay? So if we have this and I want to ignore the log, I just have to find the exponential of it. Is that okay? That's the natural log. So this thing can actually go off like this. Then of course, I can remove the negative here and bring it to the other term here. So I can cancel this negative and bring it here. Is that okay? And because I am interested in making only the I the subject, I'm going to get I on I naught. And if you find the log of it, sorry, the exponential of both sides, that is going to give us the exponent of negative alpha LC. Is that okay?
It's clear now.
So we make subject, then that is all. That is how we want it to get.
Okay, thank you.
Should we go on? Is it a little bit clear? It will not be full clear, but at least is it a little bit clear? When you read, maybe it will be clear. Mm.
It's clear. It's clear.
So now, if that is the case, I want us to try this question. Maybe you try question 1 and question 2. Question 3, we'll do it later because I have to tell you something about total uh, coefficients. So only 5 minutes. Let's try this thing out. Please, are we doing it? Hello, are we doing it?
Yes, sir, you are doing it.
Okay. It seems we are keeping. So this one, you are just going to use, you see, we have this formulas here, and the question now is asking us to find the relative intensity of the transmitted light. Is that okay? Relative intensity, we are almost looking at the transmitted light itself, the BT. Is that okay? So if that is the case, we can literally use something like this to solve. Something like this to solve the last one. Is that okay? But this time around, we are interested in finding the I over I naught. That is going to be our relative intensity. Is that okay? So this is what I'm asking you to calculate for. So if you have I over I naught, it means it's going to be an exponent of what? The negative alpha L. And you know, because the question didn't state any C, that is the concentration, we can just ignore the C to be 1, then we can just use this formula to solve. Is that okay? In the question, we've been given the absorption coefficient, we are given the length or the path length, that is the distance that the light traveled in the medium. So we just substitute, then you find it. Please, do we understand?
Yes, sir.
I was asking
So I have zero.
this, but I think you didn't hear me. I was saying you should go over the last point again
Yes, yes,
before you give us the question.
Okay. Hello. Hello. Yeah, so what was this?
So for I over I naught, I have 20.21, but I don't know what to do again.
That is all. We want to just find the relative transmitted light.
Okay.
Now, if the I over I naught, the answer is the same for everyone. If
I
the
have
answer the same for everyone.
21.21, so I don't know the rest. So the rest should talk.
Please, who again has answered for the I over I naught? Okay. Or we are still doing it.
So I had 0.5613 approximately.
5613. Okay. Any different answer?
Please, did you use the formula I over I naught? Hello.
I said
Yes.
yes, because I over I not here. You take the natural log of the powers and then you get it. So I over I naught is the same as the transmission, right? And
Very
it's
good.
given it as E power, the coefficient of it, multiplying by the length. Okay. So you just substitute in the formula and then you get it.
Please, sir, please write it here so that we all see how it is done.
That was what I was trying to explain here. So it's
And
I
but let's
over
put in the figure. I want to know which one is I not, how it is done. So that we all see how it is
we are
done. So
not
that we
finding
correct
for
them.
I and I naught. We are finding for I over I naught. What is the transmitted rate? I over I naught represents T. Because so that is what we are interested in. Is that
And what
okay?
I'm saying is that since we have the figures, let's put in there and then you write it for us to see so that
Yes,
we'll
so
know
no.
the
Yeah,
correction.
I'm explaining. I know I'm
Okay.
explaining.
Okay,
So
sir.
that is what represents the I over I naught. Is that okay? So the transmitted light is what the question is asking for. We want to find for I over I naught. And as of now, we know what I over I naught represents in terms of the coefficient and in terms of the length. Is that okay? So now we know that anytime you are giving something like this, it's just going to be the exponent of the negative alpha, that is the coefficient of absorption coefficient, multiplying the length. Is that okay? And I'm saying that we're supposed to get a C attached. But since the question didn't ask, our C is just going to be 1. Is that okay? So supposing we don't have any concentration factor in there, and it's 1, that is all. So we're just going to be substituting our parameters in there. And the first parameter that was given was the coefficient. And now the coefficient here is, let me see. We have the coefficient to be 0.1650, and we have the length to what? 3.5, which is actually long. 3.5 meters is very long. But anyway, that is what the question is saying. So we can just substitute it in. So we have negative into bracket. That is 1 point, 0.165. Then it's going to multiply our L. The L here is giving us what? 3.5 meters. And please, something like this, you have to make sure they are all in the same unit. So here, this is per meter, this is meter, so it's fine. Then you just calculate for this. And I think when you calculate, you're supposed to get 0.56, I guess.
Yes, that's the answer.
Okay.
So say you just say please wait to let me multiply and see, because I want to know how it is done before I become 0.
So just point your calculator, exponent.
I should write exponent.
So there should be an exponent there.
Yes.
You can first multiply the 2. So do that and let's see.
Okay. 650 times 3.5. Hey, me, I had 5.1.
What
Please,
you said,
how did you point your E?
I just point the exponent.
There is if you are using the scientific calculator, there is, before you get to the from the log, the next one you see that there's E power X, and that one you press shift and then before you put in everything.
I was looking at the exponent down there beside the answer.
No, be the E.
So I had 1.78.
1 point. No, it's supposed to get 0 point something.
Hey, yes, way. The exponent has come, and I 0.7. Yes, dear.
You didn't bring the negative, that's why.
Yes, supposed to. So after the exponent, I should bring negative.
There's a negative in the this in the formula.
Okay.
So you have to apply negative to the 0.165 before you get an answer.
Okay. Okay, so I have 0.561.
That's perfect. So that is going to be our relative intensity of transmitted light. That is most important. Now, when we say a brief description of a selective absorption, can someone help me with the first one? Let's say a line or two. What is selective absorption?
Yes, sir.
Hello, sir.
Can I go on? Or
how do I go on?
Okay, so selective absorption is when a material absorbs some of the wavelengths of an incident light. Or we can say that selective absorption is when a material absorbs some of the colors of what the incident light more strongly than the others.
Okay. Thank you. That is very fine. Is that okay? So later on, we will go on to the question 3, but I have to show you something before we do the question 3. Now, right after, say, absorption, there is another phenomenon that also happens that we call the scattering. And scattering is very, very, very common. It's okay. Most of the time, it's not very dominant, but it's very, very common. And when you're talking about scattering, it's just when light is deflected to a different path. Is okay. You are not ready to absorb it. You are not ready to say reflect it in a particular angle, but we will just deflect it in any angle that we want. Is okay. So scattering is different from reflection. Is okay. And you know when you're talking about reflection, we expect that the incident angle is supposed to be the same as the reflected angle. Scattering, it doesn't happen that way. So, and a very typical example is what I have down here. Light is coming from this end, and when it hits a particle, or say an atom or molecule, anything, it will just deflect at any angle at all. Is that okay? Under scattering, we can actually group it in so many categories. And one particular category that we mostly grouped it in is elastic and inelastic scattering. Is that okay? And I'll be explaining these two very, very soon. Now, even under elastic and inelastic category, there's another category that we can also group in that we call the Thomson scattering and the Compton scattering. Is that okay? Which I will also be explaining it very soon if there's a need. Is that okay? Now let's talk about the elastic and inelastic. That is the most important thing here. Now, when I'm talking about elastic scattering, I'm talking about when a photon leaves a molecule in the same energy state. Is that okay? But an inelastic, when photons loses energy, and you know the molecules will end up in different quantum states. Maybe let me use a schematic here to explain. You can see that when we have something like laser pointer, when we have something like the inelastic, our molecule was, or the atom was at the ground state. It gets excited. Is that okay? It goes to something like we have something called the virtual state. Virtual state, it doesn't reach a single state. It is halfway the single state. That is the virtual state. Then right after there, goes back to the what? To the single state. Is okay. So that single state, that range that it went is what is the elastic scattering. Is that okay? But you know, when a scattering happens, and right after leaving the singular state, move to the virtual state. But instead of it to go back to where it left, it doesn't. Is that okay? It will lose or gain a form of energy one way or the other. Is that okay? Because of the different quantum states that it engages itself to or reaches. Is that okay? Or better still, it will leave at a particular range of a single state, go to a virtual state, and instead of it to come back to its original end, extend to a different what? Single state. Is that okay? So that is what differentiates between the elastic and the inelastic scattering. Is that okay? Because whatever being the case, for the elastic scattering, we expect that when photon leaves, it's supposed to end up in the same energy state. But here, when the photon leaves, it doesn't end up to its same energy state. It will end up in a different energy state. And of course, there are a lot of examples when it comes to the elastic scattering and the inelastic scattering. Is okay? Which we'll be looking at even some common parameters that causes this elastic and the inelastic scattering. And they all have some information that they provide. Is okay? Which we'll be looking at very soon. Please, should I go on?
Hello, sir.
Yes, madam.
So please, where can we put the beryllium scattering and then the Roman scattering?
I'll come back to that.
Okay, sir.
No.
Thank you.
So should I move on? Are we okay? Should I move on?
Yeah.
Yeah, should I go on or there's a question?
Talk about the last part.
Come again.
Talk about the last part after the after the virtual state.
So this is the virtual state, and this is
So
the
yeah,
singlet.
I want the second one. The second one.
This one.
After yes, please, this one.
So
The
okay.
last one.
So you see, even for every single state, it has different grounds in there. Is that okay? And every virtual state too has a ground. Even the first state too has a different levels. Is that okay? Now we are saying that anytime a photon leaves a molecule, is that okay? We expect it to go and come back to its state that it were before. But interestingly, it doesn't happen like that. Is that okay? So instead of it to say leave here and come back to this end, it doesn't happen like that. It leaves and end up to a different state. Is that okay? And here we call it the quantum state because it's within that singular state. Or better still, it will leave and drop back to that singular state, but it doesn't end up here. Is that okay? And they're saying that anytime this kind of thing happens, it means that we are experiencing something we call the inelastic scattering. But of course, if it tends to leave and come back to where it was originally is in the same quantum state, then we call it a what? Elastic scattering. Is that okay? So have I answered your question?
Yes, sir. Yes, sir.
Perfect. Now
Thank you,
let's
sir.
go on to, okay, sir. Now we can, of course, relate these two things, the absorption that I've explained and the scattering that I've explained. Is that okay? We can relate it in terms of something we call the a whole coefficient, total coefficient. Is that okay? So supposing we have a material here and we have an incoming light, it's incidented on the material. We expect scattering to happen. We expect absorption to happen. We're expecting transmission to happen. Now, with the absorption, it will absorb what it wants. It will allow what to go through, and it will scatter some of the light one way, the other. Which, of course, there's a formula that we can use to represent all these three things that we're talking about. And here, what we have to put in mind is the same formula, but this time around, we've added another coefficient. Exactly. So first, we're having only the absorption coefficient here, but now we've added the scattering coefficient. And in fact, these two coefficients here can also be represented with a total coefficient. Exactly. So sometimes a question will come, and instead of the absorption coefficient and the scattering coefficient, they will ignore it and they will say the total coefficient is this, and they will just represent it by the total coefficient. Exactly. So what I'm trying to say is what we have here as this is the same as what? Total coefficient. So total coefficient can be same as alpha, the absorption coefficient, plus the what? The scattering coefficient. Exactly. So I didn't add the formula here, but just take note of it. There's another question, but I don't know if I should. Okay. So let's use 5 minutes to do this before we go on break. Okay. Or better still, let's do this. Let's go on break for like 15 minutes. Then as we are on break, let's use the time to solve this and this. Is that okay? So when we come back, then we just go through. What do you think? Am I online?
Okay, it's a good idea.
Uh-huh. So we are solving these two questions. So or better still, do a screenshot of this. We can solve the number 3 here. And I think if you have I shared this slide, if not, just do a screenshot of this, then solve the last one, the number 3. Have we done that?
Yes, we've done that.
Then let's solve the number, this one, the objectives here, 1 to 6. Maybe do a screenshot. Then the last one will be this one. But I'll still be online in case you want any help. Then tell me. So 15 minutes break. So we'll be coming back exactly at.
Before this one, I couldn't screenshot and you send me.
Madam, please come again.
No, before this one, the objectives one, I couldn't screenshot.
Mm.
Okay, I've done that.
Okay. So I beg exactly. Uh, let's say by 9:30 I'll be starting. So 20 minutes break. By 9:30 I'll be starting. Exactly 9:30. I beg you. So
So
let's
please,
use the time. Come again.
after this question, the last one. Okay.
So 9:30 I'll be starting.
Okay.
Hello, sir. Oh, colleagues, is it not time?
Yeah, I'm here.
Sir, the time is past. You said 9:30. It's now 9:32. So if you can continue.
Any feedback? Maybe let's go to the objectives. What did we get? So number one is in the Lambert's law, absorbance is directly proportional to
B.
B.
Concentration and path length.
Okay, perfect. Then let's go to the number two. Which process involves conversion of absorption light into heat energy?
Absorption.
Absorption, perfect. Then this thing I've not really shown, but maybe did I discuss this? No, I didn't. But let me solve.
The rate of intensity is inverse proportional to the 1/4 of the wavelength.
Yes, it's going to be C. So this is C.
That will be C.
Another C. This is B. But later on in the slides, I'll show this thing very well. Then which process is responsible for light appearance of clouds?
It's
This
B.
one to it, but it's supposed to be B, the mere scattering. Then there's another one that is here. This one you should know in absorption versus scattering, the total attenuation coefficient is expressed as
B. That is
B.
the scattering plus the absorption.
Yes.
Coefficient of scattering and coefficient of absorption.
Addition. Thank you. The number of lines in absorption spectrum is invariably more than the emission in the emission spectrum. This one's supposed to be false. I'll explain this one to later. Then I think maybe we have to go back and solve this particular one. That is talking about the scattering coefficient and the total coefficient. But before maybe I do that, I'll go on with the slides. If I have enough people here, then I'll come back and solve it. Is that okay? So that most of us will not miss it. Okay, so let's go on. So in absorption in solid and liquids, there has been so many experiments to do that. To the level that as of now we even have systems that can actually measure absorbance for us. We call it a spectrophotometer, and we actually have one sitting in our lab. Okay, so this thing now, as we talk, it's not something like a configuration you have to arrange. We buy it like a system, place it in the lab, and use it for absorption measurement. And when you do the absorption, it can measure the transmittance. So for you, you can also use it for concentration measurements if you are doing concentration experiments quantitatively. So let me just break that system down. Basically, in the system, it comprises of a light source and a lens and a slit, and our medium is here, and another slit comes in, a lens comes in. We have our slit sitting here. So this is just for the slit on the medium, and we have another lens here, and we have a dispersive medium here. A last lens cam and the screen comes in. So supposing we have a white light here, and in fact, this system configuration can be rearranged in so many ways. I've seen one system where instead of having the white light pass through like this, we have a dispersive medium in here to select the different wavelengths for it to pass through it individually. And as a matter of fact, most of the systems works in that perspective, so that only red will pass through, only orange will pass through, and as it passes through, there's a detector at the other end that is measuring it. Exactly. But the whole idea that you have to put in mind is for this kind of measurement is two things that is mostly needed. We need a light source as L. We need the sample itself in between here, and we need the detector. Exactly. So the light source is coming at different wavelengths here. It's going to pass through the medium, and our M here is a medium, and there's a detector that is going to measure it. Exactly. That is the basic idea. Now, other things that we are just going to add up is a peripheral component in optics to enhance our measurement. Exactly, accurately. So that is why you have something like slits there, you have something like prisms there, you have something like lenses in there and all. Exactly. So our light source here says a white light source, and we have our lens here to focus the light source pass through the medium. Then when you finish, you have another light source, of course, to sorry, this lens here is to collimate it. And we have another lens here that is to focus it to the prism, to the slit. Then when you do that, there's another light source here that is just going to open it and collimate it to our detector, sorry, dispersive medium. That is the prism lens. And now we focus it again to the screen and we get our light. So at the end of the day, we're supposed to know what is going in here, like the light source that is going here. So all the wavelength is going through. Okay. So at the end, you measure the ones that it didn't go through from this end, depending on the results that we get. Exactly. And that is going to give us a very interesting results. Now, if you remember, when we were discussing absorption in gases before, I showed you this kind of a thing when I told you that anytime we have a medium that is a medium that light is passing through. So let's say we have a gas, and before that, maybe we don't have any gas at all, and light passes through a prism. We expect a continuous spectrum, something like this. Is it okay? But supposing this time around we have so no gas, light passes through nicely, continuous spectrum. But supposing we have gas in between the light source and the prism, there's going to be an absorption. Is that okay? And this absorption is going to be read like this. Now, there are something called absorption lines and the emission lines. And that is what I want to explain here. So now the absorption lines here are the lines that the gas actually absorbed. Is that okay? And in fact, after absorbing, it re-emits them again. Is that okay? And that is what we have here. As a matter of fact, experimentally, when we observe the emission lines and the absorption lines, we're supposed to get more lines at the emission than the what that of the absorption. Because as it absorbs light, there are so many different quantum states that it could re-emit to. Is that okay? So here we could observe that the absorption lines is the black lines here. In the normal sense, if it re-emits, we're supposed to see all of them at that particular black end. But it's not going to happen. We could get more than that. Is that okay? So anytime there's an emission line, we expect that emission line is supposed to be more than that of the what? Absorption line. And in fact, sorry, and in fact, every material behaves differently when it comes to its absorption line. Is that okay? Of course, the absorption line is supposed to be very simpler. When you're talking about the absorption, it's very simple. See, when you're talking about something like this, it's very simple as compared to the emission. Is that okay? But even with the emission line, that is where we have something like the D lines and other ones in there, which we will not be looking at. I'm just adding it up. Yes, service mark.
Okay, sir, please, so what accounts for more emission lines than absorption lines? Say.
Okay. So let me draw this. So you see, when an atom is at the single state like this, we have different energy state levels that it's here. Is that okay? So anytime it absorbs, it moves to a higher energy state. Is that okay? And that is what gives us these lines. Is that okay? So different forms will happen. Now, when it stays there for some time, it's not stable, so it get de-excited. And the process of getting de-excited and coming to this end, that is where we get the emission lines. Now, because during the emission lines, different factors could happen. It could be that it will not even reach the singular state here or the ground state. It may even end up at the quantum level here. It may even end up in a virtual state. It could even end up in the ground state, but in the different quantum level of the ground state. Is that okay? So it may attract different more lines during the emission spectrum. Exactly. So at the end of the day, we expect yes one absorption to go, but during emission, a lot of things will happen there, and we may get extra lines comparatively. Is that okay? So we may get more lines at the emission than the what than the absorption. But nevertheless, we have to also know that during the absorption, it's very simple as compared to the lines are very simple as compared to the emission. Emission can be a little bit complicated when we are talking about the emission line spectrum. Are you okay? Service one.
Yes, sir.
Uh-huh. So should I go on now, beg? Should I go on? Hello, am I online?
Yeah, I think
Yeah,
yeah.
please continue.
It's continuous,
Okay.
sir. Mm.
Is that okay? But nevertheless, the most important thing too that we have to also know that the absorption line is very simple as compared to the emission line. Is that okay? So experimentally, when we are doing it, even we did one experiment with sodium light. And sodium light, in fact, within, I don't know if I can observe it here, within 5, 8 something, I think this end, during absorption, you may see something like this. But this chart didn't add it. But during emission, this band that you see, we have something we call the blue lines. Here is separated into two. Is okay. So you see one here, and you see another one here. And in fact, the difference between them is about 0.6 nanometers. If the spectrometer resolution is not very high and the grating is not very high, you will not see anything at all. A boom, like it will come together as one light. But if you're able to get a very good resolution, you see the very nice two lines being separated. Is that okay? So the emission lines, yes, we get it more because of a lot of things going on in there. Is that okay? But the absorption line comparatively is very simple. Simple chat and everything, then we go away. Is that okay? But when you're talking about mono atomic gases, how they behave is different from how these alkaline metal vapors behave, and even how diatomic gases behave, how polyatomic gases behave. Exactly. They all behave differently. As far as there are different materials, the absorption is going to be different. The emission is going to be different. Is that okay? So we have to put that in mind. And most of the times, the mono gases, they are very distinct. So all these ones are monoatomic gases. So you can see that something like the helium, the sodium, all of them, they are very distinct, like what we are seeing on our screen. So you see the very nice pattern and colors and other things. When you bring some of these dye and poly, you'll be very confused. It's okay. There are a lot of bands, which is very confusing. And some bands, you have to be very careful so that you can disintegrate them and observe them very well. Exactly. So all of them bring their own property. But at the end of the day, what I want to communicate in this chart is, whatever being the case, the absorption line or the absorption spectrum is very clear enough. But the emission lines are more than that of the absorption lines. Now, there's something we call fluorescence. Is that okay? And before I explain fluorescence, maybe let me explain. Yes, sir.
So the diagram, is it reflecting that they are more than what you are showing us right now?
What is more than?
The previous one, please.
No, this one, for this chart, the emission is not reflecting that. Is that okay?
Uh-huh.
The
Okay.
emission is nearly the same as the absorption, because where you
Okay.
see it absorbed, that is where you see it emitted. Where you see it
Okay.
absorbed, that is where you see it emitted. But
So let me tell you,
experimentally,
yes, in our various secondary school, can we actually demonstrate this for them to see? Is it possible, or our labs are not equipped to do that?
yeah, we can do it, but this one you need a spectrometer.
Okay.
Even the university levels too that we teach students, the
Okay.
interestingly, the spectrometers are not
No,
enough,
not okay.
because as of now, my optics lab, we have only about 4 working spectrometer. You can imagine a whole UCC having 4 working spectrometer for
Okay.
students to.
Okay.
So,
Okay.
but if your school is near UCC, every
Okay.
year, physics, we do this outreach where we go to secondary school for them to appreciate optics. So we
Okay.
have some case that we reach out to students, let them see some lenses. We have
Mhm.
some lenses that they can use their hand to observe it, like a telescope. So
Okay.
like a clear telescope and other things, so that at least they appreciate
Okay.
interference, everything. Yeah, we have these
Okay.
things that we do outreach. So if your school is close to UCC,
I'm
anyone
far,
on
far
the
from
floor
you.
can reach
Far,
out.
far away from you. I'm far away
Ah,
from you.
too
Volta,
too bad.
Volta Street.
Uh, Maybe one day when we
Okay,
get money, we
thank
can
you.
come there. The person can just reach out to me, then I'll talk to the
Okay.
FISAC,
That's okay.
then we collaborate, then come to your school, come and teach them some. It's only notice that
Okay.
we can do
All right.
basic things, and they will appreciate. Mhm.
Okay. All right.
Okay.
Thank you.
You're welcome, sir.
Thank you, sir.
Okay. So now there's another thing that we call fluorescence. So now I've explained absorption, I've explained scattering. Is that okay? And the scattering too, I've explained some phenomena under scattering. I'll come back to it again. But let's just do a brief outline here and look at fluorescence. Fluorescence is very interesting phenomenon. I'll not lie to you. And the applications are tons of them. Is that okay? So in a normal sense, we expect that when light is incident on a material, is that okay? Any matter you can think about, we expect that, of course, it will absorb some. But the question is, after absorption, what happens? Is that okay? So after absorption, there are a lot of collision that goes on in there, because the molecule is excited, or the atom is excited. So it tends to vibrate very well. Is that okay? At that end. And right after the collision, something happens, and that is what we call the emission. Is that okay? But there are two things that can cause the emission. And the condition is, if the collision happens before the emission, then the energy is changed to another form of energy that we call the heat. Exactly. But if collision, there's no collision that happens, there's something that is released. And that one is another form of energy, but this time it's in the form of a radiation form. And that is the light emission. Exactly. So supposing the incident light on a material, the molecules in there or the atoms in there tends to vibrate or get excited. Is that okay? And because they are very excited, their lifetime is very, very short. It needs to transit to another thing. Is that okay? But if there's a collision that will happen after the excitation, then we should be expecting something like a kinetic energy to happen right after the collision. But if it gets excited, and no collision happens at all to the atom or molecule, then it means that this atom or molecule will regenerate something or release something to us. And that is in the form of a radiation called what? The light or the photons. Is that okay? So this thing is very important. And in releasing this light or the photons, one particular form of the light or the photons re-emitted is what we call the fluorescence. Is that okay? So now the fluorescence, before I explain the fluorescence, do you know this Calic rosary that they use? Have anyone in Calic, or maybe we've seen it before? Have you seen it before?
Yes, sir.
Yes, sir.
Very good. And you can see that anytime you are in a maybe someone wearing it enters a dark room, what happens to it?
It starts to produce its own light.
Perfect.
Or
It glows. Yes, it produces its own light. Exactly. And interestingly, in physics, that thing that happens, we call it phosphorescence. Exactly. And the thing is, the material is such that anytime light is incident on it, it absorbs this form of energy. It gets excited. But during the excitation state, no collision happens. So it doesn't convert it to energy. Because of that, it re-emits it in the form of what? Of light. Is that okay? But the re-emission of light that is going on here, this time around, it takes time to re-emit the light. In fact, it takes a lot of time to re-emit the light. Is that okay? So you can see a rosary that can actually glow like a minute. Some glows to like seconds, minutes. It will not reach 1 hour though, but like you get some glows to a minute. Is that okay? And that one is phosphorescent. So it will take its time to dissipate the light small, 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 small. And in fact, the anticoupler that we used to use, that is the same phenomena behind it. So there is this cation and anion inside there. And you know, when there are some voltages that are applied, there's a zinc sulfide on that screen, that glass screen. Behind it, not where that you watch. Inside there, there's a zinc sulfide there. And when there is that excitation and the zinc sulfide gets excited, it glows. Exactly. And if you remember, J.J. Thomson experiment that he did, he used the same phenomena. So he was having behind the anode, he was having a zinc sulfide there. And anytime there is high energy in a vacuum, of course, there's high energy from the cathode to the anode, and there's a small leakage in the anode to the zinc sulfide. You will see a sparkle. Exactly. So that sparkling that he was seeing was letting me know that okay, there's something called a cathode ray, and that brought about to that electron. Exactly. That small thing, that sparkling, exactly. That's okay. It means there's something going on. Because as a matter of fact, you can't use your eye to see. So that was a bit of what we are learning now. Is that okay? And that is the bit of the phosphorescence I'm also talking to you about now. Are we following? Hello.
Hi.
The way it is
yes, sir.
quiet.
Yes.
Are we following or we are confused? Should I go on?
Sir, please go on.
Okay. So that is the phosphorescence. But you see, phosphorescence
Sir,
takes, yes, sir.
please, sorry, with the explanation that you were giving earlier
Mhm.
concerning you said when a molecule absorbs energy, then it becomes a, and then assuming no collision occurs, then the energy is converted into kinetic energy. And then in the slide, you have into brackets heat. So I wanted to understand, is it the kinetic energy that is still equivalent to the heat energy? Or
Yes,
how are
yes.
they? Oh, okay.
Mm. So you see, kinetic energy, we are talking about motion, movement. Is that okay?
Yeah.
And
Yes.
when there's movement, it causes heat. Is that okay? Because of heat collision and heat jumping up and down. Is that okay? If you're supposed to dive more into this, we'll be looking at the vibrational and the rotational, but we don't have to go there. Is that okay? So the kinetic energy is the heat that we are talking about.
Okay. All right, sir.
Silent, are you okay?
Yes, please, sir.
Mhm. So now let's look at this chart. So there's a chart that we call the Jabrowski diagram. Is something like what I have dubbed from internet to this end. What I have here. So let me use a laser pointer. So you see, this is our ground state. This is our singular state. Is that okay? And the atoms there, if light is incident on the material, it absorbs the energy. It goes up here. Is that okay? So it reaches there, it wants to give off the light again. And I told you that there's something we call the phosphorescence that can happen. And that one, it takes time before it re-emits. There's another one that doesn't take time at all. Right after the absorption, it's be re-emitting it. And in fact, the time of the re-emitting is about nanoseconds, which is very, very short. And that one, you can use your eye to see like the fluorescence. Fluorescence can take seconds and minutes. Is okay. So you can see that the substance is glowing. But the fluorescence is not like that. It's within nanoseconds. So you need a very powerful detector to actually detect fluorescence. Is that okay? It's very, very short. And that is very important. Is that okay? So plenty things happen. Scattering is happening, another thing is happening. But a general overview is that a fluorescence too can happen in after absorption of what? Light. Please, are you okay? I want to move to the next slide. Now, that is for gases. So even under fluorescence in solid and liquid, there is something we call the Stokes and the anti-Stokes. Is that okay? And the whole thing about fluorescence is anytime that there's a re-emitted emission of light. Okay, there's hands up.
Sir,
Yes, sir.
is it
Fast.
for example solids and liquids or solids and gases?
Come again.
Is it fluorescence in solids and liquids or solids and gases? Because we are done with gases. I can see solids and gases again.
So I think it's solid and liquid.
Thank you, sir.
I think it's solid and liquid. But I don't know. Anything that we're explaining here, they are all related to all the matters. Is that okay? I didn't hold on. I didn't specify it here. Maybe it could be solids and gases, though. I didn't really specify it. Anything that I'm explaining here can be related to solid, gases, and the liquid. It's the absorption that varies when it comes to the gases and other things, but here it's relatively the same. Is that okay?
I'll give her.
Thank you. So under the fluorescence, now we understand fluorescence, but under the fluorescence, there's another interesting thing that actually happens. And there is something we call the Stokes law, and we have something we call the anti-Stokes law. And what the Stokes law is actually doing is anytime that we have light that is re-emitted, we have it at a longer wavelength than the absorbed light. So, and it makes sense. And this thing is the same as having a lower energy than the high energy. So supposing you give the material a light of high energy, you don't expect it to give you a relatively the same high energy. Is that okay? So you give it a high energy, it will give you a lower energy. Is that okay? And this is very, 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 very common when you are talking about something like the in scattering. Is that okay? Where we have the Raman scattering and the sorry, yes, see, still the Raman scattering, but the Stokes and the anti-Stokes. Fluorescence too can behave the same way here. Now, what we are saying is, if you give it high energy, don't be expecting it to give you the same energy or a more energy. It will give you a lesser form of energy. Is that okay? And here, what is just trying to say is, yes, if we have a longer wavelength and you give it a shorter wavelength, anytime you have a shorter wavelength, it means you have high energy. It will give you a longer wavelength. It means if it gives you a longer wavelength, that means it has given you at a lower energy. Exactly. And that is what Stokes' law is just trying to define. So if I do a measurement, let me write. I do a measurement, supposing this is my spectrum. And the energy that I've given, this is the wavelength, and say the wavelength is starting from 300 nanometers here. And this is 400 nanometers here. And this is, say, 500. And supposing this is my intensity, supposing I give a particular wavelength of 400 to a sample, will my fluorescence happen here or it will happen here?
It will happen behind.
Behind that is the 500 or the 300.
I think the 300.
The 300. Okay. So I have number 1 for 300. Who again will go for 300?
The work 500 after.
I said, Bismarck, you've already chosen your answer, or you want to go another one?
I say after the
After.
yes.
So here rather. Okay. So apart from say Bismarck, who again will go? So if we give 400 unlimited to our where will the re-emitted light fall? Is it going to be at 300 or 500? Sir Michael. Sir George.
I've talked already. I said
okay.
to be below.
It will be below. Okay. You said below, and Bismarck said, okay, that's fine. Then, Sir Michael. Settle the ties.
Sir, you didn't label the axis, so I don't know which one is which. So the axes are not labeled. Which one is the wavelength? And which one is the?
So this is the wavelength. Down here is the wavelength. The 300, 400, 500.
Okay, are the wavelengths. Okay.
And the top here is the intensity. Is okay. And I'm saying that I've given a wavelength of 400 to the sample.
Okay, 400 to the sample. Okay.
Where would the ray emitted be at?
It should be around the 500.
It should be around the 500. Yes, that's perfect. The answer will be around the 500. So
yes,
the 500 is at longer wavelength.
Wavelength, yes.
The 300 is going to be a shorter wavelength.
Wavelength.
On the Stokes is saying that re-emitted fluorescence light always has what a longer wavelength than the absorbed one. And even in our chart here is evident. Always we have Stoke to be represented here, and the anti-Stoke is represented here. And fluorescence will always follow the Stokes law. Is that okay? So always we have the re-emitted light to be what? At longer wavelength. Is that okay? That is lower energy. But the anti-Stoke can happen in scattering. Anti-Stoke where we leave it a particular wavelength, but this time around it will give us what? A shorter wavelength. So you can imagine giving a sample of low energy and it will give you high energy. That is the anti-Stoke. Is that okay? Now let's go on. So yes, I've explained this. So still on the Stokes law, absorption happens here and emission follows. So supposing this place was our 300 nanometers, we will get our emission as around what 500 or 400 or anywhere that you want. Is that okay? But at the end of the day, you're supposed to get it out at a longer wavelength. And of course, we can find the change in the wave in the shift, wavelength shift. Is that okay? So we measure the absorption, we measure the emission, we can find the emission. And in fact, this Stokes has been used to do a lot of studies in terms of how the energy or the molecules of a particular matter behaves. Is that okay? So the fluorescence the phosphorescence to have explained. Is that okay? So this time around, there will be a little persistence in the re-emission of light. Is that okay? And that is what gives us the fluorescence. And I told you that this one, there's a delay in the emission, which it has been stated here. So we are talking about lasting for like minutes, seconds. Is that okay? And the process like this is called the phosphorescence. So please don't exchange these two things. It's two different things on its own. We have the fluorescence and we have the phosphorescence. So now, after physical optics, you see someone wristband glow or someone watch glow, or you see any olden TV model that is not LED. This ethical pole, then you see it glow. This is the things or mechanism that has to come in mind, that there's something that is going on there, and that is what you call the fluorescence or the phosphorescence. And now you can know that, okay, this is phosphorescence going on. Is that okay?
Okay, sir.
Yes, sir.
Can you relate this to which one? The fluorescence, there's the tungsten bulb and all that, or it's a different principle?
It's actually the same. So
Okay.
the fluorescence bulb and everything is the same. There's a
Okay.
medium there that is being excited, and at the
Okay.
end we give us the blue color. So I was going to go to that slide where
Okay.
we have application of this fluorescence light,
Okay. Okay.
and most of them is this UVM. And you know this thing is actually used in medical side a lot. Is okay in terms of sterilization and other things. Now there's even a white teething procedure that we use the UV to do that. Exactly. So you go there, the incident some light on it. That is the fluorescence light. Then of course it remove all the dents and everything from your teeth and everything. So it has a lot of its own application. And even if you want to authenticate the CD notes that you are holding, they put it under a particular UV light and they'll say that, oh, okay, this, because when you put it there, we expect it to glow. Is that okay? Some feature supposed to come out. So it comes and say, okay, it is authentic or you are using a fake money. Is that okay? So it has quite a wide application one way or the other. Now, there's another question that we have to do and before we go on to this, the Roman scattering. Can we do a screenshot of this? We'll come back to it. So we have about two certain questions there already. So let's do a screenshot of this. Or should we do it, then go? I don't know. How do you want us to proceed with this?
So I think I'm just adjusting. We do one of them before you proceed.
Okay. So maybe only 5 minutes. Let's start. Let's do only the objectives up to this end. I believe you can do this. I believe you can do this. I believe you can do this. But this one, I don't know. So maybe you do the last one too for me. And let me see how you understand this. So we do 1 to 5 and 9. Yeah, hello. Are we done? So the number one is re-emission of absorbed light at the same wavelength as the incident light is called.
Resonance radiation.
Okay. So resonance radiation, and I think I have it here. So resonance radiation, here's it. So the gas will emit absorb light at the same what wavelength as the incident. I already mentioned it, but I have it here. So that one is resonance radiation. And we have another one. According to Stokes' law, the wavelength of fluorescent light is always
longer than the absorbed.
longer than absolute light. Perfect. So in gas, if collision between molecules is infrequent, the absorbed light is re-emitted as what?
Phosphorescence.
In
Resonance
gases.
radiation. Resonance radiation.
So in gases, what's the meaning of infrequent?
Is it not so often? Or
Okay. So if collision is between molecule is infrequent, the absorbed light is re-emitted as what?
So is that not longer wavelength or something like that?
that's resonance
It's,
radiation.
resonance radiation comes in if we have the re-emission the same as the incident light.
Yeah.
So if we have a collision that is not happening after an absorbed light, what will happen?
That's
You see, when you say
phosphorescence.
very good, that would be phosphorescence. Is that okay? If collision do happens, we expect something like heat to happen. Is that okay? If no collision happens, we expect something like phosphorescence or what? Or so it's going to be phosphor or fluorescence.
Fluorescence,
Is it
yes.
okay? So when you see fluorescence, the answer is correct. If you see phosphorescence, the answer is correct. Is that okay? So a solution of fluorescence in water absorb the blue part of white light and emit. If it absorbs the blue part, what will it emit?
The red
It
light.
will emit red light. This one, the question is very dicey.
Violet.
In fact, when it absorbs blue light, it can re-emit green too. It can re-emit red. It can re-emit, as far as it can re-emit a longer wavelength than the absorbed one. That is fine. So the question here, when you choose red, that is correct. When you choose green, that is, but when you choose violet, it's wrong because violet has a shorter wavelength than the blue. Okay. And even when you choose infrared too, you may be marked correct. So the number 5, the delayed re-emission of absorbed light lasting for seconds or minutes after source is switched off is called. This is simple.
The phosphorescence.
Phosphorescence is okay. Perfect. Now let's go straight to the last one, the number 9. So this one, phosphorescence, this one, I said this is correct, this is correct, this is correct. Then this one we said the answer is what? Longer than the absorbed. Then here we said the answer is what? The number 1, the answer was what? The B.
Resonance radiation.
Resonance radiation, thank you. So so when you're talking about Stokes' law, is it always true in all cases?
Sir, no.
No, sir. Not always true.
Perfect.
Yeah.
Because there's something that we call the anti-Stokes. Is that okay? So there's no way Stokes' law can hold in all cases. Is that okay? Okay. And under the anti-Stokes, what type of scattering happens there? Do you remember?
Shorter
There.
You
wavelength.
said we have thermally excited vibration states.
No, look
That
at the
is
type of scattering. Can you see? So under the anti-stoke, the type of scattering that happens there is what? Or we can see it's Raman scattering. Is that okay?
Okay, Ramas. The screen is gone.
Ah, sorry. So now let's look at particle sizes. When we are now, let's hold on to fluorescence. We are going back to scattering again. Let's talk about particle sizes when we are discussing fluorescence, scattering. Sorry.
Say,
It's yes, sir.
please, I want to ask a question before we proceed. On the question 3, it said that in gases, if collisions between molecules are infrequent, the absorbed light is re-emitted as, and I think the answer we chose the phosphorescence. But then I was asking, is phosphorescence about delayed emission or is about infrequent collisions?
So you see, when light is absorbed, we spoke about two things that can happen. We spoke about the fact that if after it has gotten excited, if it collides, it means that the energy is going to be transferred to heat. Is that okay?
Yes,
but
sir.
if there's no collision, the energy is going to be transformed in the form of a light, that is photons. Is that okay?
Yes.
And here from the question, it means after it has absorbed, there's no collision. It's infrequent. Is that okay? And from the observation, no, from the answers that it has been given to us, none of them meet that criteria apart from fluorescence. Is that okay? Because after there is no collision, we expect light to be re-emitted. And from the situations that we have here, none of them covers light re-emission apart from the fluorescence. I don't know if I'm able to convince you enough. So here, what is happening at the heat aspect is if the collision happens, is that okay? And I think maybe the infrequent here is very confusing. Maybe there should be no or yes collision so that the answer could have been straightforward. Is that okay? But as far as we are saying that collision happens, we should get heat. No collision happens, we should get light. You have to look at the options and check which one was the best one for us.
Sir.
All right.
Yes, sir. Yes, service mark.
Yes, question 4. What at all is that fluorescein? That what the solution fluorescein? What is it?
Solution of fluorescence.
Fluorescein. What is it, please?
So any liquid that can actually absorb light and give it to us back is a solution of fluorescence. And I don't know the example that I can give to you. There's a particular liquid that we dip in water and it allows it to fluorescence. Maybe let me share a screen and Google something and show it to you guys.
And then secondly, is blue not close to violet in the spectrum? Why?
Okay. In fact, violet comes before blue, I guess, right?
Yeah. Yes.
So it means that violet has a shorter wavelength than blue.
Okay.
And in fluorescence, we expect that we should be getting a longer wavelength than the absorbed one. Okay. And here, if blue is absorbed, there's no way we should be getting the re-emitted as violet. Okay. We should be getting a longer wavelength of colors, like the red, like the green, like the, even if it's possible, like the infrared.
So this one, I think, is not about emission. The question is still on absorption. No? If you read the question very
the question is saying a solution of fluorescence in water absorbs the blue part, of and emits. So after absorbing, what does it emit?
Okay.
Exactly. So we want to know the light that emits. Yes.
Okay. All right. Okay. Well noted. Then that's okay.
let me stop this one. I wanted to show you something, but yes, Sir Francis. But hold on,
Say, come
sir,
again.
are
Come
you
again.
okay?
Come again. Say, please come again about the solution of fluoride. He said is what example is water.
Okay,
I'm not getting it.
I'm coming. So the question is, we have a solution of fluorescence in water, and we are talking about water that can fluorescence. Is that okay? It's like the rosary that can glow, phosphorescence. So we are talking about water that can fluorescence. And now we incidented a white light on it, and and it absorbed only the blue light. Is that okay? And after absorbing the blue light, we are saying that which color will it re-emit, or will it emit at all? Is that okay? And from our explanation from fluorescence, we are saying that for fluorescence, only Stokes' law should work. That is, if we give it a shorter wavelength, we should get a longer wavelength. Is that okay? If you give it a lower energy, you're supposed to get a, so when you give it a higher energy, you're supposed to get a relatively low energy. So we are saying that with all the options that we are giving here, it means that anytime we are given a situation like this, the light should re-emit a light that is longer than the one that we gave it earlier. Sapphire, are you okay?
I'm okay, but I want to see the video.
You wanted to see the what?
Then you say you are going to show us a YouTube
Yeah, I
video.
wanted
I want to see
to. No, you can just
the type of
Google.
the type of solution.
You can just
Okay.
Google water fluorescence or any water that fluorescence. It's just a liquid that when you set incident a blue light on it, it will fluorescence one way or the other for you to see. Is that okay?
So there's no an ordinary water.
It can be an ordinary water that is induced with a fluorescence dye. Is that okay? So it can be a normal water, then we just did a drop or two with something called an induced fluorescence. Then it will go for us.
Okay, thank you.
Yeah, yes,
Hello.
say anything. Yeah.
So please,
Mm.
I understood that when there is a re-emission of absorbed light at the same
Mhm.
wavelength as the incident light, that is when we are talking about resonance radiation, if I'm correct.
Perfect. Yeah.
All right. Then, just to get some clarity here,
Mm.
when we have infrequent collisions, I think that
Mhm.
is the same thing as fewer collisions. Is that correct?
Yes. So I think this question is very, very dicey.
I,
So
I was
it's
I wanted to
okay.
actually come from a certain point of view so that so
Mm.
if there are fewer collisions, then doesn't it suggest that there will be very few, let me say, minimum energy loss?
Mhm.
And so for that matter, it will be about the same wavelength that will be re-emitted
Same wavelength that is re-emitted.
because of fewer
Okay.
collisions, which will bring
Let's
about less energy loss.
maybe I'll look at the question again because for resonance radiation, uh, there's few collision that is going on. So one way or the other, being heat emission or light emission, resonance can actually plays a role here. So yes, I think we can actually also bring in resonance in a situation like this. Yes. So it's true. Instead of the phosphorescence, the answer can be B, I think. Yes. Class,
Say,
what do you
does it
think?
mean that
Yes. Mm-hmm.
say does it mean that there's influences?
Mm-hmm.
You are that there's no collision, or
There's no
there's collision
collision.
but fewer one.
Yeah. In fact,
Because
we
we
don't expect pollution to happen in fluorescence at all. As far as we absorb. Mm-hmm.
so this
Come on.
one it happens, but it is fewer. The
Yeah.
collisions happen, but it's fewer. So
Yeah.
can we say that is resonance?
Yes, and I'm saying that yes, for resonance can come in here. Is that okay? So Sanafi is drawing our attention that if we are talking about, say, absorption and collision, and I just referenced from the resonance radiation that at lower pressure, we should be having some few collision here. But you see, the question didn't state about low pressure, but as far as we have some few collision in the question, the answer can actually fall under resonance radiation. Is that okay? Yes.
So I
Some
was trying
answer.
to check the answer. I was trying to check the answer from but
Mhm.
I said the answer is resonance radiation.
Oh, okay. Then let's go with the resonance radiation. In fact, I personally I wanted to see something like a lower pressure before the resonance come in. That is why I was advising for the phosphorescence. But I think since we don't expect any collision at all in a situation like this, maybe the phosphorescence too may be out. Then we'll go with the resonance radiation. Is that okay?
Sir, if that is the
Yes.
case, when I also check, I had fluorescence. So
That's
fluorescence,
something that,
when
yeah, the
collision
person is
are
quite.
rare.
So I would
Uh,
suggest that we hold on that question. Maybe the next
yeah,
time
let's go on to the question.
we
Then I'll just work on. I just wrote it, so I'll just work on it. Then uh, I'll bring it again. Is that okay?
Thank you, sir.
But it's good. At least we are all contributing. It means we understand what is going on. Yes, so it's good. We are all deliberating on it. So
Say,
mhm.
say,
Yes, sir.
does it mean that in fluorescence,
Mm-hmm.
collision, because we said that when collision is rare,
Mm-hmm.
in rare means when you say it's rare, there is mean that infrequent. Like, but we said that when collision is, we check, he said that when collision is rare, the starting state of the molecule isn't quenched by energy transferring collision. Okay, so if you say maybe you think about it, we can think about it, but
Yeah, the whole point is in re-emission of energy like radiation, we don't expect collision. Collision comes in when something or different form like a thermal is coming in. That is the heat. Is that okay? So, in fact, there has been a situation where there's a collision where we get something like heat and we still get the radiation again, but that is not our level to go to. It's not really of importance now. That is where I was saying we have something like the vibrational and the rotational energy. We don't have to go there. So the two is very dicey and the question is dicey. So I'll just reframe the question very well to fit what we are trying to understand here. Is that okay? Mhm. Have we all agreed on that so that we go on?
Yes,
Yes,
sir.
sir.
So yeah,
Mhm.
from
Let
here,
me go.
sir,
Yeah.
question 3.
Mhm.
We have established the point that because it is clearly stated that few collisions also, the same
Mhm.
as rare collision, infrequent. So I think the more appropriate answer should be the phosphorescence as we have
Mhm. Okay.
discussed.
You don't
Yeah.
worry. I'll just reframe the question very well to fit
Okay.
what we understand. Is that okay?
All right.
Mhm.
Okay.
I'll reframe
Sir,
it.
But
Yes, sir.
I think we should also re-emphasize that with the phosphorescence, there is
Mhm.
emphasis on delayed re-emission.
Mm.
So we should also factor that in our analysis. Bismarck.
so sir,
If there is
I say,
delay, if
I
there
think
is
we
delay,
are,
please, can I come in?
Yes, I'm
boss, I
listening.
think we are mixing
Let's
the
move on.
two.
Let's
We
move
have
on.
fluorescence, and we have
Mhm.
resonance. We are saying this is
mm,
fluorescence, it's not phosphorescence. We say
mm,
phosphorescence, then we mean a different thing. But this is fluorescence. That's what we mean.
yes,
You chose fluorescence.
Yes, that is what, because that is the case. That's the only case when the emission is fewer. When collision is few or infrequent.
yeah.
Sir Bismarck, I will
Yes, sir.
just reframe the question to fit.
Okay, that's okay. That's
Is that
okay,
okay?
sir. That's okay,
I
sir.
think this is. I was trying to tighten our thinking, but I think it's confusing us more. But but it's good we are all bringing this thing on board. At least we understand what is going on. Is that okay? Okay.
Yes, sir.
So now let's look at the sizes of particles when it comes to scattering. Is that okay? So as of now, you know that when light is incident on matter, absorption can happen, inflation can happen, infraction can happen, scattering can happen. And in fact, this scattering that we are talking about is very, very, very dependent on two factors here. Scattering radiation is dependent on one, the refractive index of the particle, and two, the particle size. And that is what I want to talk about here. The particle size is very, very important. Is that okay? And as of now, we all know what elastic scattering is, and we all know what inelastic scattering is. I've explained that earlier. And under the elastic scattering, we have the relay scattering. An example is the relay scattering, the Debye scattering, and the mean scattering. Now, what is going on uh, with the relay scattering is that anytime we have relay scattering, we expect that the particle size is supposed to be way smaller than that of the what? The wavelength of the light. So if the wavelength of the light is 300 nanometers, we expect the particle size to be lesser than 300 nanometers. That is relatively very, very small. Is that okay? And you saw a question where relay scattering was, the intensity was related to wavelength. And here it's related as what? 1 over the what? The raised the power 4 of the lambda. That is the wavelength. Is that okay? So it means that anytime we have shorter wavelength, extremely shorter wavelength, we expect intensity to increase. Is that okay? Meaning there will be more scattering. Is that okay? So blue light will tend to scatter very more than relatively like what? Red light, because of their inverse of proportionality. Is that okay? So shorter wavelengths will have more intensity scattered than the longer wavelength. And in fact, this relay scattering is the best phenomena that actually explains why the sky is blue and why when the sun is settling down, it appears to be the red color that we see when the light is settling. That's beautiful color. And you know, because of the droplet that we have there, which is relatively small, like super, super small. So because of that, the blue light will tend to scatter because the light that is from the sun, it has all the wavelength colors. It has the red, the violet, the green, all the colors you can think of. But because blue has relatively shorter wavelength than the red, it will tend to scatter more. So we tend to see more of the blue than any other color. But as it's settling down, this time around, the distance do matters here. Is that okay? So as it's settling down, the longer wavelength tend to penetrate more than that of the what? The blue. So we tend to see what? The blue sunset more when it's settling down. But the relay scattering is opposite as the near scattering. Now, the near scattering, we are saying that anytime the particle size is relatively the same as that of the wavelength, that is where we have what? The, the, the near scattering. Or, in other case, when we have a larger particle size than that of the what? The wavelength. Is that okay? And now, that near scattering can actually explain the fact that where we have the clouds to be white, and in a situation like this, we don't have one being dominant than the other one. They all just scatter equally. Is okay. And the very example is the aerosol and the other large molecules up there. Is okay. So the red, the blue, the green, they are all scattering what? The same. Is okay. One is not going to scatter more than the other one. And I think Madame Fisher was talking about the beryllium scattering and the Raman scattering. And I think this is where it comes. And they are all under what you call the inelastic scattering. Is that okay? And it's still dependent on their different wavelengths and the different quantum states that they actually force on. Is that okay? There's this man, he's an Indian. In fact, there's in UCC here, there's two people that has enjoyed his work. My senior colleague and the current VC. They have this yearly program that they do at India, and to honor his work, he is dead anyway, and he is one of the pioneers of Raman scattering, and his name is C.V. Raman. So they have this Raman scholarship that they give to people worldwide every year. And if you are doing any work related to Raman scattering, they tend to invite you and we work with them. And I think there's a lot of money in there and other things. So he did a very wonderful work in terms of scattering, and he helped with the discovery of this Raman scattering. And Raman scattering actually behaves in terms of the Stokes and the anti-Stokes, where we have some form of energy, we give it to it, and it comes back to a different. Am I online? Hello.
Yes, the screen is not showing. Online.
Oh, the screen is not showing.
Oh, so it's showing
I see
here.
my screen.
Okay.
It is
Oh, okay.
showing.
Oh, okay.
It's not showing.
It is. I can't see anything.
Okay. You can go off and come. Madam Felicia,
Sir,
I don't know if you can
It's
go
not
off
showing.
and come or you.
I've gone for about 1 hour.
Do you have a mountain close to your
It's
house or
not
a tree that
showing.
where
The
you
Yeah,
can
screen
I'm
is
in
climb?
the
not
mission
showing.
house, so I stay at the mission house.
Oh, then there's no tree there or mountain I can climb.
But then
There's no tree or mountain I can
Let's go
climb
on.
for
Let's go
there
on.
is 3 years. I'm really suffering. I can't see anything at all. I can't hear.
Oh,
What kind of
yeah, the class is being recorded, so maybe when we are done,
Okay.
you can just do it.
Okay, sir.
Mhm. So when you're talking about Raman scattering, it's actually a type of inelastic scattering. Is that okay? And as I said earlier, discovered by the CV Raman. And what this one is doing is relatively not the same as the relay scattering. Really, when we give it this amount, it goes and come back to the same one. Is that okay? It's different, way, way different. And we expect that anytime we have relay scattering, it corresponds to the vibrational energy levels of the molecule. So most of the times, studies that are done with Raman scattering is to study the vibrational energy of the sample, which talks a lot about how the sample behaves. Is that okay? So how different is Raman scattering and fluorescence? That is the question today. So in terms of the light that is incident on its condition, the first thing that we can talk about is Raman scattering. In Raman scattering, I'm reading this one. In Raman scattering, the incident light wavelength does not have to match with the absorption band of the materials. Is that okay? And even with the Raman tool, we are talking about a virtual state. In fluorescence, it will go up to the singular state before it gets de-excited. Is that okay? And in fluorescence too, we expect the material to go at first absorbed. So it has to absorb a material first before it gets excited. And the intensity wise, Raman is very, very weak. Is that okay? So if you want to do Raman scattering, you need a very powerful detectors and instrument to do that. Is that okay? And usually, as I said, it needs a sensitive instrument or photograph to detect it. Exactly. So people that are working around Raman are really doing well. Exactly. Because you can get fluorescence and Raman scattering, a little of Raman scattering is in there. You have to do a lot of work before you remove the fluorescence and get the Raman scattering. Exactly. In fact, there are two basic theories that can interpret Raman scattering. The first one is the viewing it from the classical point of view and checking it from the quantum point of view. Is that okay? And if we are going to do these two things, it means the quantum, you have to look at the light in the form of a photon, and in the classical, we have to look at light in the form of electromagnetic wave. Is that okay? And if we are considering the material to be polarized. When you say polarized, it means the energy or the electron cloud can easily be distorted, exactly, be changed. It means that anytime you have a high polarization of the material, it means the Raman will scatter more. It means you get more Raman scattering, exactly. And if the polarization of the material I'm talking about is very low, it means the Raman will be very weak, exactly. So in a situation where we have soft molecules like benzene that is having a high polarization, it means it will scatter more. And a situation where we have hard molecule like water will scatter very weak. Exactly. If you want to also look at it in a form of a quantum level, we can also describe it in that perspective, where if you are saying Raman scatters occurs when the photons interact with the molecule and exchange, which will lead to scattering of a shift. Is that okay? And this time around, we can relate it in terms of high or low frequency. Is that okay? And we can use that one to determine how the vibrational or the rotational energy level of the molecule actually behave. Is that okay? So we can look at this in two points of view. But I don't think there will be a question that will dive you more into this. Is that okay? But it's less for you to appreciate that the fact that you can look at Raman scattering in the classical point of view and in the quantum point of view. And I have another question for us to look at. I think this would be, is it the same question? Okay. This one.
Yes, it's the same question.
The objectives are not the same, I think. Or even this one is the same. So the number 1 to number 3, they are different. According to Stoke, this one too is the same. But anyways, let's go through this one briefly. Let's go to the number 1 and 3. 1, 2, 3. So in Raman scattering, the scattering light differ from the incident light because of.
I think it's B. B.
Very good. It's going to be because of the change in molecular vibrational energy. Is that okay? And it's stated here. The vibrational energy. Is that okay? Now, the number 2, we did it before, understood. But the number 3, which type of molecules are strong Raman scatters?
Molecules with high polarization, high polarizability.
Very good. Soft molecules. And a very typical example is the benzenes. Is that okay? Okay, so perfect. Now let's go back. Yes, let's go back to the very first question that you were supposed to do before the break. We didn't do it. Hey, where is the question?
It was the previous one. Yeah, this one. The number 3.
Okay, so the number 3 and this one. Did we do it?
Yeah, we did this one. Only the number 3 that we didn't do. Yeah, number 3. The previous one, number 3.
What about this one?
This one too. Okay, this one didn't solve it too.
Okay.
We didn't solve it. We
So
didn't do the number 3 and the number 4.
And the number 4. Okay, that's fine. So let's use, it's left about 15 minutes. Let's use the 15 minutes to go through it ourselves. Is that okay? So I'll end the class, then we'll go through it ourselves. Then next week, before we start, I'll just ask about the answers. Then we move on. So far, we are left with only 2 units to go. So by next week, I'll do that. Is that okay? We will finish. Say if your hands is up.
Oh, sorry, it's an old hand. Sorry.
So any questions so far before I end the class? So unit 5, we'll do the fraction and we continue. Okay. Any question before I end the class?
No, sir.
Perfect. Okay. So I'll. Yes, madam. Yes, madam.
Please, I saw something here, application of Raman scattering. I don't know if because I went off. We have about 11 applications here in the manual. I don't know whether they will be asking us to be writing the application or anything. I just want to know.
No, let's just read it, and it's for you to appreciate what Raman has done. I think I should have added it to the slides, but it skipped me. So maybe I'll just update the slides and add it. Is that okay? And maybe I'll talk some more about it so that you appreciate it. Is that okay?
So can we end with that one?
Yes.
Like, can you explain this one
Okay.
before?
Then let me share the. I don't have it in my slides, so I'm coming. Let me open the PDF and share
Okay.
that section. It's at page what?
Page 110, 110.
110.
Yeah.
110, 110. Okay. Okay. I've seen it.
Okay.
So let me share the slide that I have. Yeah, the PDF. Okay. So Abel, can we see my screen?
So media, whatever you do, I can't even see.
Okay. So I'm just checking what you have, the book. So the first one is talking about the fingerprint of chemical structures. So you see, every molecule or every material, or in fact, every matter has its specific molecule that it contains. And every molecule behaves differently. Is that okay? In as much as we are all blacks, our skin color can never be the same. Our genes that we have, our DNAs, everything can never be the same. Is that okay? So one particular application about Raman scattering is knowing the chemical fingerprint. When you say the chemical fingerprint, the spectral signature. Is that okay? So as a now, we know the chemical fingerprint of water under Raman. So anytime we see a spectral, we know that okay, this is benzene, this is say water, this is say ethanol, this is say methanol, any chemical at all. Is okay. And in fact, this studies has actually moved on to the process of say identification. So if you know the fingerprints, we can know that, and you don't know the material at stake, you can just take the data or using the Raman scattering, then we can know that okay, this material contains water or benzene or anything. And in fact, Raman scattering has developed to this stage where we have a system for it. So we have a Raman system that measures Raman scattering data for us. Exactly, which is very important. So the applications are tons. And in fact, the applications of Raman scattering is not only basically on scattering. My work I am doing in UCC here, I'm doing fluorescence studies. And we have something we call autofluorescence. And that one too has a tons of applications there. We can in fact also find for the chemical fingerprint of materials using fluorescence. Is that okay? And even using Raman. Is that okay? The Raman is very delicate than the fluorescence. So if you are doing fluorescence, at least fluorescence is difficult, but it's not as difficult as the Raman. Is that okay? Because you have to get a very sensitive optical component to do that. And another thing is also finding for even the stage of the anions and the cations of some fluids. Exactly. Raman scattering can do that. And if you want to identify, say, the crystalline of polymorphs, that one too can do it. So with the identification of different materials, and because it can measure their vibrational state, it can look at the stress, the orientation of the molecules, and even study, say, high pressure, temperature, and other things in the substance. Is that okay? So when it comes to the applications, madam, don't do babare, just it's just an exploration of what Raman has been used to study in our current world to let us know that it's not a theoretical thing we are learning. It's a typical application that we apply now. Is that okay? In our world today. Are we okay?
So what about that? Is it LSEP at the end of every this thing? What does that mean?
No, that one, don't mind it. I think they
Okay.
copied it from somewhere and they pasted it here. So
Okay.
it gives that sign. It depends on the person's computer. So don't mind anything at the end. When most of the times you copy text from somewhere and you paste it somewhere, that is how it appears. Okay. So I think I'm good to go now. I'll share. I'll update the slides, then I'll share it to everyone. Is that okay?
Okay, sir.
And I think MTN sent a message that there will be an internet outbreak and issues after 10 o'clock, after 11 o'clock. So let's be careful with it if we have another class, and let's get a good place to stand for internet. Is that okay? Just in case. Okay.
Okay, we have class at 7 o'clock.
Okay. So have a nice day. Thank you.
Okay, thank you, sir.
Okay. Colleagues, please, when are we starting with the group studies on? Because this semester, the things we are doing and the network is not favoring some of us. So. And the pressure in the house and the programs piling up. No man, Erasmus, Benjamin, Bismarck, George, what are you doing to us?
Maybe when you are done with everything, maybe when you are done with, or maybe you can suggest a day that we can meet. Kojo Anefi, Emmanuel.
I think what our brothers.
We can't hear you.
I said that on my wife.
What they hear me, I'm a crossing lady now, Casano.
Anefi, please, me see. Anefi, please call me later. Call me. We'll discuss something. But I'm saying that
All right.
we can schedule a group discussion then. In the meantime, the past person will also help. Even if you don't have it, let's go and fish for it and come and discuss it. We are sure that at least about 50% of it can drop. So that at least that 50% you are able to get it. Then you will add more to it. So I beg, Madam Felicia, you if you call the lecturers, they can help you.
Yes.
If you call the lecturers privately, they
To
can
be frank
help.
with you, physics lectures are difficult to deal with than chemistry teachers. Because chemistry lectures, the moment you ask them to give you tutorial question, they will give it to you, and the tutorial question that they will give, that is what they will set the question from. But physics teachers will not give us tutorial questions, and they will not give us anything to know anything about.
No, I think one reason could be that most of the
the physics that we are doing as a major, we are not the results are not good than the chemistry results, and I don't know.
And I think if we can get somebody from Madam Eloy,
I'm there, Papa. I'm not going to cry.
Please, where you have been doing online and then purely online classes with the UCC students, kindly contact any of them. They can help you. For them, because they are on campus, getting those questions wouldn't be difficult. They can go to the department, and even they have people who print and even sell. So at least.
To be frank with you, I don't even know who is a visit student at UCC now, unless I ask.
Usually when we meet online, okay, we'll try that. The next time we have a general lecture, the one that we have with Madam Abigail or so, or any of them. During the lectures, we can ask the question across that place. If there's any physics teacher, physics student from UCC, the person should just DM you, or the person to identify himself. Then we can contact them. For them, they can get it. When they go to the department, they can get it.
Okay. I think the other hand to be here. I don't know whether some of them are here or not. I don't know.
On the other hand, too, you can also try this one. The coordinators, center coordinators.
Okay.
The center coordinators. When you,
Madam.
Yes, for the center coordinator, the moment you contact them, they will see that we are solving, so they will change the question because they are setting the question. Yes.
No, center coordinators don't set the question. So.
Oh, okay. I thought the coordinators themselves.
No, center coordinators, they are just like headmasters or headmasters.
A guy called Kojo on their feet. He has all the tutorial questions. Just keep his number. He will give you everything that you want. You don't have
so
what are you saying? Francis, what are you saying?
Oh, Francis, this is not something you should joke with.
We are serious.
Somebody is called Kojo, so I should call him. Is he part of us?
No.
Yeah, he's here. He's here.
He's a biology student.
He's here. But Francis, this is very
joined this group.
serious. when Madam Felicia called Kojo and Anefi doesn't give it out, he will think that maybe he has it and he doesn't want to give it.
Yes.
But she wanted help.
But Anefi is
No.
here, so you can defend yourself. Do you have
Madam, you just like
one.
you.
Not to talk of all. I don't even have one.
Yami whom?
I mean that you have some.
Me?
So I think, Madam,
Yes,
you can use your influence. You are a lady. And when ladies make demands, it's difficult for guys to reject the demand. So I beg, use your influence. Try and get in touch with the physics students, especially those who go to lectures at UCC. They can help. And I think there are those who usually get the questions, then they bring it late. Some of them bring it in the morning that we are going to we are going to write the mock, the quiz, or the exams itself. That's what they do. I beg, if there's anyone from UCC here, or if you go to code office at UCC, they will give you. They don't need it for anything. So when one of the letter was saying that because they may bring it, no, they don't have. It is a past question. So if it's a past question, no lecturer want to hide past question from students. So if we have people from here, other than that, what we have to do is that we contribute and give money to one person. The person go to campus and then get us all the past questions, at least from now till we yes. From now till we yes. I think that one will also help.
Okay.
That one will also help.
And then another one too is that those who knows the previous student, the first batch, if you know them, some of the science students, at least you can contact them. Those who know some of them, so that you can get the question from them straight away. So that is another one too. But I'll be calling and see. In fact, the moment we finish with this one, after next week, no Monday, Tuesday, we have to start with group study. So I'm begging you.
Okay, madam. Okay,
Yeah.
madam. So that one is a point well made. So from now till next week, let's try. Now that we are on vacation, we have final week till school reopen.
The vacation is not helping us so because of the teaching practice. Some of us they are loading us here for them.
Go and tell them at your school. Okay, maybe. I don't know
They
how
don't
your
have teachers.
discussion.
They want to give you everything. They don't have teachers.
Okay. At Kaswade.
But you shouldn't forget that this evening, 7 o'clock, we have another lecture with Yusuf.
Okay. So thank you very much. Please use your influence. You're a lady. Use
I will try.
Use your influence. Thank you.
Thank you. I will try, and I'll be asking too. Okay. Have a nice day.
Same to you.